Welcome to the Late Lab. It's wonderful to have you here. Before settling in, it would be lovely to know where you're watching from tonight. Maybe you're tucked beneath a blanket, listening in a dim room. Maybe you're on a late journey home, with the world sliding quietly past the window. Or maybe you're simply resting somewhere peaceful, letting the day loosen its grip one small thought at a time. Wherever you are, hopefully you're warm, comfortable, and ready to wander gently into one of the strangest quiet chapters in cosmic history. If you enjoy these calm little journeys through science, leaving a like and subscribing really does help the channel grow. And to everyone already here, already subscribed, or returning for another sleepy exploration, thank you. Your support helps keep this small corner of the universe drifting along. Tonight's subject begins in a place with no sunrise, no constellations, no glittering galaxies, and no familiar night sky at all. So with any luck, it should be peaceful enough for sleep, though, admittedly, the idea of an entire universe waiting in darkness before the first stars appeared may be just interesting enough to keep one eye slightly open. A gentle cosmic hazard. So let's begin, shall we? What was the universe like before the first stars began to shine? Look up at a clear night sky, and it can feel as though stars are the natural state of the universe. They seem almost permanent, scattered quietly through the dark like tiny pinholes in a vast black curtain. Some burn with a blue-white intensity, some glow with a softer amber warmth. Some are hidden from the eye but still present, gathered into galaxies so distant that their light began travelling long before human beings, forests, oceans, or even the Earth itself existed. It is easy to imagine that the universe has always been this way. Dark space, bright stars, galaxies turning slowly in the deep, a grand, silent arrangement of light and distance. But the truth is stranger, and in some ways much quieter. There was a time when there were no stars at all, not a single one, no sun, no Milky Way, no constellations, no galaxies filled with soft spiral arms, no glowing nebulae, no supernova remnants, no planets lit by distant suns. If there had been eyes to look around, which there were not, there would have been no familiar night sky to see. And yet this was not a universe of simple emptiness. It was not a cold, finished void waiting politely for someone to decorate it. The universe before stars was young, expanding, cooling, and full of ingredients that had not yet become recognizable. It contained radiation. It contained matter. It contained dark matter, an unseen form of matter known through its gravity rather than its light. It contained tiny differences in density, faint irregularities that would later become enormously important. These small variations were the quiet beginnings of future structure, the first hints of where galaxies would one day gather, where stars would ignite, and where planets would eventually form from the ashes of earlier stars. This early universe was not visually dramatic in the way a galaxy is dramatic. It did not have the kind of scenery that makes a telescope image look like the universe has hired a lighting designer. There were no jewel-like star clusters or glowing clouds of gas shaped by stellar winds. But physically, it was rich. It was active. It was changing. Every later galaxy depended on it. Every planet depended on it. Every ocean, every mountain, every forest, every living cell, and every observer quietly wandering about the sky depended on conditions laid down during this early dark era. To understand that time, scientists use the Big Bang model, which is the central scientific framework for describing the early universe. The name can be a little misleading, because it sounds like an explosion. It can make the mind picture a bright blast bursting outward into empty space, like cosmic fireworks with unusually ambitious career goals. But the Big Bang model does not describe matter exploding into a pre-existing emptiness. It describes space itself expanding. In the earlier stages, we can meaningfully study the universe was hotter, denser, and more compressed than it is today. As space expanded, the universe cooled. As it cooled, it passed through different physical stages, each one making the next possible. This idea took time to emerge. One of the key early figures was Georges Lemaitre, a Belgian physicist and priest who proposed that the universe was expanding. He understood that if galaxies are moving apart today, then the universe must have been denser in the past. Around the same period, Edwin Hubble studied distant galaxies and found that their light was shifted in a way that showed they were generally receding from us, with more distant galaxies receding faster. This became powerful evidence that the universe is expanding. Not expanding from one central point into surrounding space, but expanding everywhere, with the distances between faraway galaxies increasing over cosmic time. That expansion matters deeply for the story before stars. A universe that expands also cools. Cooling allows new things to happen. At first, conditions were too hot for ordinary atoms to exist. Particles moved in a dense, energetic state, and light could not travel freely through space in the familiar way. Later, as temperatures dropped, atomic nuclei could form. Much later still, electrons could join with nuclei to make neutral atoms. Only after that could light travel more freely through the universe. Even then, there were still no stars. The first free-streaming light was not starlight. It was the ancient glow of the hot early universe itself, stretched over time by cosmic expansion. So the first stars did not appear immediately. The universe had to wait. That word, wait, is of course a human word, and the universe was not standing around checking a clock, perhaps tapping one cosmic foot. But from our point of view, there was a long sequence of necessary steps. The universe had to expand, it had to cool, it had to form the simplest atomic ingredients, it had to become transparent to light. Then gravity had to begin its slow work, pulling matter into slightly denser regions, deepening those regions, and allowing gas to collect in the invisible gravitational well shaped by dark matter. Gravity is patient, which is fortunate, because the early universe required a great deal of patience. The matter spread through space was not perfectly uniform, but the differences were extremely small. Some regions were just a little denser than others. Over time, those denser places attracted more matter. As more matter gathered, their gravity became stronger. This is one of the most important ideas in cosmic history. Structure grows from tiny beginnings. The largest galaxies, the richest clusters of galaxies, and the vast web-like arrangement of the universe all trace back to very small early irregularities. The universe before stars, then, was not a blank stage. It was more like a dim workshop in which the tools had not yet been lifted, but everything needed for later construction was already present in some early form. There was hydrogen, the simplest and most abundant element. There was helium, formed in the hot early universe. There was dark matter gathering under gravity into the first invisible scaffolding. There was radiation, cooling and stretching as space expanded. There were tiny density variations, not yet galaxies, not yet stars, but not meaningless either. They were the first unevenness from which cosmic architecture would grow. This is what makes the pre-stellar universe so fascinating. It asked the mind to imagine a time before the most familiar symbols of space existed. Space, to most people, means stars. Even darkness is usually understood by contrast with them. The night sky feels dark because the stars shine through it. A galaxy seems beautiful because its glow is surrounded by blackness. But before the first stars, darkness was not a background. It was almost the entire visible story. The universe had not yet learned to shine in the way it does now. And still, hidden inside that darkness was the future. The atoms that would one day enter stars were already present. The gravitational seeds of galaxies had already been planted. The laws of physics were already at work quietly and precisely, without any need for drama. Nothing like Earth existed. Nothing like a human eye existed. Nothing like a warm room, a telescope, or a sleepy person listening late at night existed. But the chain of events that would eventually make all of those things possible had already begun. So when the stars are seen as ancient, they are indeed ancient by human standards. But they are not as ancient as the universe itself. They arrived after a beginning, after a cooling, after a first glow, and after a long darkness. The first stars were not the opening sentence of cosmic history. They were more like the first lamps lit in a house that had been built in silence, room by room, long before anyone could see its shape. Before the first star, the universe was already becoming, not brightly, not quickly. Not in a way that would have looked spectacular from the inside, but beneath the darkness, space was expanding, matter was gathering, radiation was fading, and gravity was beginning to sketch the outlines of everything that would follow. To imagine the universe before the first stars, it helps to go even further back, before darkness had settled into the deep calm of empty-looking space. The earliest universe that science can describe was not quiet in any ordinary sense. It was not a black open sky waiting for stars to appear. It was extraordinarily hot, unimaginably dense, and expanding with a speed and intensity that makes most everyday words feel a little underqualified for the job. This does not mean the universe began as a fireball bursting into a surrounding emptiness. That picture is tempting, partly because the phrase Big Bang sounds like something loud happened in a place where nothing had been happening before, but the scientific picture is stranger and more subtle. The Big Bang model describes the expansion of space itself. It is not matter flying outward from a central point into a waiting void. It is every region of space once being much closer together, much hotter and much denser, and then space expanding everywhere. There was no outside edge where the universe was rushing into darkness like smoke from a candle. The universe was not expanding into a room. It was the room, the walls, the distances, and the rules by which distances could grow. In those early moments, the universe was so hot that familiar objects had no chance of existing. There were no atoms, no molecules, no dust grains, no rocky worlds, no gas clouds gently collapsing towards stars. Conditions were too energetic for the ordinary architecture of matter to settle down. The universe was filled with particles, radiation, and intense interactions, all packed into a state far denser than anything found in daily life. It was also, on very large scales, remarkably smooth. That smoothness is one of the great clues in cosmology. When astronomers look across the observable universe today, the large-scale pattern is surprisingly even. Galaxies are clumped locally, of course, because gravity has had billions of years to gather them together. But the early universe, as seen through its oldest light, was almost the same temperature in every direction. That is not what might be expected without some explanation. If different regions of the early universe were far apart and had never had time to exchange energy or information, why would they look so similar? Why would the ancient glow of the universe be so uniform across opposite sides of the sky? This question is one reason scientists developed the idea of cosmic inflation. Cosmic inflation is a widely studied theory suggesting that extremely early in cosmic history, the universe underwent an astonishingly rapid expansion. This expansion would have happened in a tiny fraction of a second, far shorter than any ordinary blink, heartbeat, or sleepy attempt to remember why someone walked into a room. During inflation, space itself may have stretched by an enormous amount, taking a very small, smooth patch of the universe and expanding it across scales large enough to include everything visible to us today. Alan Guth is one of the central figures associated with the development of inflationary cosmology. In the early 1980s, he proposed inflation as a way to solve several puzzles in the Big Bang model, including the question of why the universe appears so uniform. André Linde later developed important versions of inflationary theory, including ideas that helped make inflation more flexible and influential in modern cosmology. Their work did not give science a finished final answer carved neatly into the side of the universe, which would be convenient if slightly dramatic. Instead, inflation became a powerful framework, one that explains several otherwise puzzling features of the cosmos, while still leaving important questions open. It is important to say this clearly. Cosmic inflation is not the same kind of directly observed fact as the existence of the cosmic microwave background or the expansion of the universe. It is a strong and widely investigated theory, supported by how well it fits certain observations, but the exact mechanism behind inflation remains uncertain. Scientists do not yet know what physical field drove it, whether it happened exactly as standard models suggest, or whether a deeper theory will eventually replace or revise it. In cosmology, this is quite normal. The universe is generous with mysteries and rather less generous with labelled instruction manuals. One of inflation's great strengths is that it helps explain the smoothness of the observable universe. If the patch of space that became our observable universe was once tiny enough for conditions to even out, and then inflation stretched that patch enormously, distant regions would naturally share similar properties. The universe would appear almost the same in all directions because it grew from a region that had already become highly uniform. Inflation also helps explain why space appears very close to flat on large scales, meaning its geometry behaves much like ordinary geometry across the observable universe. But inflation does more than smooth things out. It also gives scientists a way to understand where the first seeds of structure came from. A perfectly smooth universe would be a problem of a different kind. If matter were spread with absolute sameness everywhere, gravity would have no slightly denser places to work on. There would be no preferred regions where matter could gather first, no early clumps, no future galaxies, no stars, and no quiet little planets where life might eventually invent biscuits and astronomy. The universe needed tiny irregularities. This is where quantum fluctuations enter the story. In ordinary language, a fluctuation is a small variation, a tiny departure from perfect evenness. In the very early universe, quantum physics suggests that small variations in energy and density would naturally exist. These were not galaxies, stars, or clouds. They were far more subtle than that. They were tiny differences woven into the fabric of the early universe, almost unimaginably small at first. During inflation, those tiny quantum fluctuations were stretched across enormous distances. After inflation ended, they remained as slight differences in density. These slight differences mattered because gravity is wonderfully persistent. A region that was only a little denser than its surroundings had a little more gravitational pull. Over time, it could draw in more matter. As more matter gathered, the region became denser still. That process would eventually help produce the cosmic web, the vast pattern of galaxies and galaxy clusters seen across the universe today. The enormous structures of the modern cosmos may therefore trace back to extremely small early quantum variations. The idea is almost absurdly elegant. Galaxies may have grown from tiny early wrinkles in an otherwise smooth universe. Of course, this does not mean the first stars appeared right away. Inflation, if it happened, belonged to an incredibly early stage. The universe still had to pass through a long chain of transformations before anything like a star could exist. It had to continue expanding. It had to cool. energy had to settle into particles. Particles had to form protons and neutrons. Atomic nuclei had to appear. Much later, electrons had to combine with nuclei to form neutral atoms. Light had to become free to travel across space. Only after all of that could gravity begin the long, patient gathering of gas into the first star-forming regions. The hot beginning is therefore not separate from the later darkness. It is what made that darkness possible. The universe began in a state too hot and dense for atoms, stars, or galaxies. Expansion cooled it. Cooling allowed matter to change form, and once the first great glow faded and stretched, the universe entered a quieter era. Not empty, but dark, filled with hydrogen, helium, dark matter, radiation, and faint irregularities waiting for gravity to magnify them. There is something beautifully strange about that progression. The first stars were not born because the universe began bright. They were born because the universe cooled from brightness into darkness. The heat had to soften, the density had to relax, space had to stretch. Matter had to become simple before it could become complex. The early universe began as an intensely hot and smooth sea of possibility, and only by expanding into a colder, darker state did it prepare the conditions for the first lights to appear. So before the first star, before the first galaxy, before the first soft point of light in the cosmic dark, there was this hot beginning, dense, smooth, rapidly expanding, and seeded with tiny variations that would one day become everything. Not a fireball in space, but space itself changing. Not chaos without structure, but a universe whose earliest patterns were almost hidden, waiting for time, cooling, and gravity to reveal what they could become. As the universe expanded and cooled, it began to move from pure intensity toward the first recognizable ingredients of matter. This was still not a universe of atoms or dust or gas clouds floating peacefully through space. It was far too hot for that. But it was no longer just an almost featureless blaze of energy and expansion. The early cosmos was beginning to sort itself into particles, forces, interactions, and tiny building blocks that would later make everything else possible. In everyday life, matter seems stable and solid. A stone feels like a stone. A cup feels like a cup. A hand resting on a table does not usually feel like a temporary arrangement of particles held together by fields and forces, which is probably for the best. Breakfast would be more stressful if every spoonful of cereal came with a full lecture on quantum field theory. But beneath ordinary experience, matter is made from smaller components. At the deepest level currently understood by modern physics, the familiar world is built from elementary particles, particles that are not known to be made from anything smaller. The early universe was filled with these fundamental ingredients. As it cooled, energy became associated with particles such as quarks, electrons, neutrinos, and photons. Photons are particles of light, though in the early universe their story was very different from the gentle starlight that later crosses the night sky. Electrons would one day become essential parts of atoms. Neutrinos were extremely light, elusive particles that interacted only weakly with other matter and could slip through the universe almost as though it were barely there. Quarks were stranger still, because they would not remain freely wandering for long. They would eventually combine into heavier particles, including protons and neutrons. The framework scientists use to describe these known elementary particles and their interactions is called the Standard Model of Particle Physics. It is one of the great achievements of modern science. It describes quarks, electrons, neutrinos, photons, and other particles, along with three of the four fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. Electromagnetism governs light, electricity, magnetism, and the behavior of charged particles. The strong nuclear force binds quarks together and later helps hold atomic nuclei together. The weak nuclear force is involved in certain forms of particle transformation, including processes important in nuclear reactions and radioactive decay. The Standard Model is extremely successful. It has made predictions that have been tested with remarkable precision, and it gives scientists a powerful way to understand matter at very small scales. But it is not a complete theory of everything. Most importantly for cosmology, it does not include a full quantum theory of gravity. Gravity is described extraordinarily well on large scales by Albert Einstein's general theory of relativity, which treats gravity not as an ordinary force, but as the curvature of space-time. The Standard Model and general relativity are both deeply successful, but they do not yet fit together into one final framework. The earliest universe sits right at the border where this missing unity becomes especially important. Even so, scientists can understand a great deal about what happened after the very earliest moments. As the universe cooled, quarks became bound together by the strong nuclear force. Quarks come in different types, including up quarks and down quarks, and combinations of these make protons and neutrons. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. Those details may sound like the universe was assembling itself from a very small set of oddly named toy bricks, and in a sense, that is not completely wrong. The names are playful, the physics is serious. This transition mattered enormously. Before protons and neutrons existed, there could be no atomic nuclei. Without atomic nuclei, there could be no atoms. Without atoms, there could be no stars in the familiar sense, no chemistry, no planets, and no later complexity. The first particles were not just tiny details in the background. They were the raw inventory from which the cosmos would eventually build structure. Modern scientists study these kinds of particles using both theory and experiment. One of the most important research institutions connected to particle physics is the European Organization for Nuclear Research, located near Geneva. Its particle accelerators allow scientists to recreate, for the briefest moments, extremely high energy conditions that help reveal how particles behave. These experiments do not recreate the entire early universe, of course. No laboratory is quietly producing baby universes in the basement, which is probably reassuring for health and safety paperwork. But particle accelerators can test physics under energies far beyond ordinary experience, helping scientists understand the rules that shaped matter when the universe was much hotter and denser. The Large Hadron Collider at the European Organization for Nuclear Research is especially famous for confirming the Higgs boson in 2012. The Higgs boson is connected to the Higgs field, which helps explain why certain elementary particles have mass. This does not mean it explains all mass in the universe in a simple everyday sense, because much of the mass of protons and neutrons comes from the energy of the strong nuclear force binding quarks together. But the Higgs field remains a crucial part of the Standard Model, and its discovery was a major confirmation of modern particle physics. One of the deepest mysteries from this early period is the imbalance between matter and antimatter. For many particles, physics allows a corresponding antiparticle. An electron has an antimatter counterpart called a positron. When matter and antimatter meet, they can annihilate, converting their mass into energy. In many simple versions of early universe physics, matter and antimatter should have been created in nearly equal amounts. If that had happened perfectly, matter and antimatter would have destroyed each other almost completely, leaving behind a universe filled mostly with radiation and almost no matter to form stars, planets, or sleepy observers wondering about particles late at night. But that is not the universe we see. The observable universe contains far more matter than antimatter. galaxies, stars, planets, dust, gas, and human bodies are all made from matter. Antimatter exists, and it can be produced in particle interactions and studied in laboratories, but it is not present in the same large cosmic abundance. Somewhere in the early universe, a tiny preference for matter over antimatter must have emerged. This problem is known as baryon asymmetry, because protons and neutrons belong to a broader class of particles called baryons. Scientists know that an imbalance exists. They do not yet know the full explanation for how it arose. That unresolved question is one of the quiet reminders that the story of the early universe is not finished. Cosmology is not just a tidy sequence of facts placed neatly on a shelf. It is a living investigation. Some parts are strongly supported by observation and experiment. Others are still being tested, refined, and argued over with the kind of polite intensity that scientists reserve for the universe's most stubborn secrets. By the time quarks had combined into protons and neutrons, the universe had taken another essential step toward the first stars, though it was still far from being ready to shine. The ingredients were still simple, the cosmos was still hot. There were no atoms yet, no transparent space, no dark calm, and no glowing points of stellar light. But something important had changed. The universe now contained the building blocks from which the first atomic nuclei could form. The path towards stars was not direct. It moved through stages, each one depending on the one before. Energy had to give way to particles. Quarks had to become protons and neutrons. Matter had to survive its encounter with antimatter. Forces had to shape the behavior of particles with extraordinary precision. Long before gravity could gather gas into the first star-forming clouds, the universe first had to create the particles that would become the simplest nuclei. In that hot young cosmos, the foundations of every later atom were being prepared, quietly and rapidly, in a universe still too young to contain even a single star. Once the universe contained protons and neutrons, it had the raw pieces needed for something more familiar, though still far simpler than atoms. These particles could begin to form atomic nuclei, the dense central cores that would later sit at the heart of atoms, not full atoms yet, not hydrogen drifting quietly as gas, not helium sealed inside glowing stars, not oxygen waiting to become air or water. Just nuclei, bare and exposed, moving through a universe still far too hot for electrons to settle around them. This early formation of atomic nuclei is called Big Bang nucleosynthesis. It is one of the most important stages in the scientific story of the early universe, because it explains where the first simple elements came from. The word nucleosynthesis simply means the making of nuclei. In this case, it refers to a brief, intense period when the young universe was cool enough for protons and neutrons to bind together, but still hot and dense enough for nuclear reactions to happen across space. The timing was delicate. If the universe had been too hot, newly formed nuclei would have been broken apart almost immediately by energetic radiation. If it had already cooled too much, particles would not have collided often enough to build anything significant. For a short window, the conditions were just right. The universe was not calmly assembling matter at a workbench, wearing tiny safety goggles, though that image does have a certain charm. It was a vast, rapidly expanding environment where nuclear reactions could briefly occur almost everywhere. During Big Bang nucleosynthesis, the universe produced mainly hydrogen nuclei and helium nuclei, with tiny traces of lithium. A hydrogen nucleus is usually just a single proton. Helium nuclei contain 2 protons and usually 2 neutrons. Lithium, a slightly heavier element, appeared only in very small amounts. These were the first nuclear ingredients of the cosmos. They were simple, but they mattered enormously, because every later star would form from this early supply of mostly hydrogen and helium. The broad picture was developed by scientists including George Gamow, Ralph Alpher, and Robert Herman. Gamow was a major figure in applying nuclear physics to the early universe. Ralph Alpher, working with Gamow, helped develop the theory of how the hot early universe could create light elements. Alpha and Herman also made an important prediction connected to the leftover radiation from the early universe, the ancient glow now known as the cosmic microwave background. Their work helped show that the early universe was not just a philosophical idea about beginnings, but a physical environment with testable consequences. The proportions left behind by Big Bang nucleosynthesis are one of the great pieces of evidence for the Big Bang model. By mass, the early universe became mostly hydrogen, roughly about 3/4 hydrogen, with around 1/4 helium and only a very small trace of lithium. The exact values depend on how the proportions are measured and modelled, but the overall result is clear. The universe began its chemical life very simply. Hydrogen dominated, helium was substantial, everything heavier was almost absent. That simplicity is worth pausing over, because it tells us something profound about the universe before stars. The early cosmos did not begin with all the elements already prepared. There was no meaningful supply of carbon, oxygen, silicon, iron, calcium, or phosphorus drifting around from the start. The ingredients needed for rocky planets, living cells, bones, blood, oceans, and breathable air were not yet available in any useful amount. The universe had made the simplest elements, but not the rich chemistry that later worlds would require. Carbon, oxygen, silicon, and iron would need stars. They would need the intense pressures and temperatures inside stellar cores, where nuclear fusion could build heavier elements over long periods. Some elements would require the violent deaths of stars such as supernovae, or even more extreme events like neutron star mergers. But before the first stars, none of that had happened. The universe had hydrogen and helium, a hint of lithium, and an enormous amount of patience ahead of it. This is one reason the title's central idea is so important. Before stars, the universe was not truly empty, but it was chemically poor. It already had matter, it already had nuclear structure, it already had the simplest elements from which stars could eventually form, but it did not yet have the chemical variety that makes the later universe feel so textured and alive. There were no grains of silicate dust, no carbon compounds, no oxygen to bind with hydrogen into water, no iron to sink into planetary cores, no calcium for shells or bones, no nitrogen-rich chemistry supporting living tissues. The early universe was full of possibility, but the possibility was still locked inside a very limited set of ingredients. In a way, Big Bang nucleosynthesis gave the universe its first simple recipe. Mostly hydrogen, a generous helping of helium, a tiny trace of lithium, and then, for the more complicated flavours, please wait for stars. It was not exactly a varied menu, but it was enough to begin the next phase of cosmic history. Hydrogen, especially, would become the main fuel of stars. When gravity later gathered hydrogen into dense clouds, and when the central regions of those clouds became hot and compressed enough, nuclear fusion would begin. The same basic element made in the early universe would eventually become the fuel of starlight. Helium also mattered. It was not just a passive leftover. Its abundance provides a powerful test of early universe physics. If scientists calculate how nuclear reactions should have unfolded in the hot early universe, they predict a universe with roughly the proportions of hydrogen and helium that astronomers actually observe. This agreement between theory and observation is one reason Big Bang nucleosynthesis remains such an important pillar of modern cosmology. It connects the physics of particles and nuclei to the large-scale history of the universe. Lithium adds a more complicated note. Big Bang nucleosynthesis predicts a small amount of primordial lithium, but observations of very old stars show less lithium than some models expect. This is known as the cosmological lithium problem. It does not overturn the broader success of Big Bang nucleosynthesis, because the predictions for hydrogen and helium work extremely well, but it does show that some details remain unresolved. The early universe, like many mysterious things, appears to have kept at least one small receipt in a drawer. Nobody has fully opened yet. Still, even after these first nuclei formed, the universe was not ready for starlight. It was not even ready for ordinary atoms. The nuclei existed, but electrons had not yet settled around them in stable arrangements. Free electrons moved through space, interacting constantly with radiation. This mattered because free electrons are very good at scattering light. Photons could not travel freely for long distances without being redirected again and again. The universe was still opaque, not because it was filled with dust or smoke, but because it was filled with charged particles that kept light trapped in a kind of restless cosmic haze. So the formation of the first atomic nuclei was a major step, but not the final step toward transparency. The universe now had the cores of atoms, but not atoms themselves. It had hydrogen nuclei and helium nuclei, but not neutral hydrogen and neutral helium in the familiar sense. It had light, but not light moving freely across space. It had the first simple chemical identity, but not yet the conditions for chemistry as it would later be understood. This stage sits beautifully between the hot chaos of elementary particles and the later quiet darkness before stars. Something had clearly changed. The universe had begun to form durable nuclear building blocks. It had established the basic material from which the first stars would eventually be made, but it still lacked the freedom, calm and transparency needed for the universe to become visually open. It was still too hot, too ionized, and too filled with scattering particles. Long before galaxies glittered, long before the first star ignited, the universe had already made its first nuclei. It had taken protons and neutrons and arranged them into the simplest elemental foundations. Hydrogen and helium were born not inside stars, but before stars, in the fading heat of the early cosmos. They were the first plain notes in a piece of music that would later become far richer. The heavy instruments had not yet entered. The melody was not complete, but the opening tones were there, waiting for space to cool, for light to loosen, and for gravity to begin shaping the darkness. The young universe had now made its first simple nuclei, but it still had not become the kind of place where light could travel freely. That may sound strange at first, because light was already everywhere. Photons filled the cosmos. Radiation was part of the universe from its earliest hot stages. But light existing and light moving freely are not quite the same thing. A lamp can shine in a thick fog, and yet its glow may not travel far before it is scattered, softened, and lost. The early universe had a problem rather like that, though its fog was not made of water droplets. It was made of charged particles. At this stage, the universe was a glowing plasma. Plasma is often described as a fourth state of matter, alongside solid, liquid, and gas, although nature is under no obligation to keep its filing system that tidy. In a plasma, electrons are not neatly bound to atomic nuclei. Instead, charged particles move more freely, and because they carry electric charge, they interact strongly with electromagnetic radiation. Light is electromagnetic radiation, so a universe filled with free electrons was a universe where photons had a difficult time crossing large distances. This is one of the key differences between the early universe and the later night sky. Today, starlight can travel across enormous stretches of mostly transparent space. A photon can leave a distant star or galaxy and journey for millions or even billions of years before reaching a telescope. Space is not perfectly empty, but it is transparent enough that light can carry information from remote places to waiting instruments. In the early plasma-filled universe, that was not yet possible. Photons existed in abundance, but they were constantly interrupted. The main process responsible was Thomson scattering. In Thomson scattering, a photon interacts with a free charged particle, most importantly a free electron, and is redirected. The photon is not necessarily destroyed in the ordinary sense, but its path is changed. In the early universe, this happened again and again and again. A photon might try to move through space, only to meet another electron almost immediately by cosmic standards, scatter in a new direction, then scatter again. Instead of travelling in a long, clean line, light wandered in a restless, tangled pattern. The result was opacity. The universe was not transparent. It was glowing, hot, and filled with radiation, but it could not be seen through. If an impossible observer had existed inside it, there would have been no distant view across space, no faraway galaxy, no sharp horizon of stars, no clear line of sight. Every direction would have been filled with the same dense radiance, because light was coupled tightly to matter. The universe was bright, but it was not open. A useful comparison is thick fog on Earth. In fog, light from a street lamp or car headlight scatters from tiny water droplets. The light is still there, but it loses its direct path. Edges blur, distances vanish. The world becomes a soft glowing wall, and everything beyond a short range becomes hidden. The early universe behaved somewhat like that in the sense that light could not pass straight through it. But it was not literally fog. Fog is cool air filled with small liquid droplets. The early universe was a hot ionized plasma made of free electrons, atomic nuclei, radiation, and other particles moving in an intensely energetic state. So the comparison is useful, but only if it is allowed to behave itself and not run off pretending the cosmos was a damp morning in November. This opacity is important because it explains why the universe before stars has a hidden period. Light from those early plasma stages cannot reach us in a direct ordinary way, because it could not travel freely at the time. The universe had not yet released the ancient light that would later become visible to instruments as the cosmic microwave background. Before that release, radiation and matter were closely linked. Photons were trapped in repeated scattering, and the universe was visually sealed from itself. The reason free electrons mattered so much comes from electric charge. Electrons carry negative charge, and photons are the carriers of electromagnetic radiation. When free electrons are loose in space, they respond easily to passing light. Bound electrons inside neutral atoms can still interact with light in many ways, but a universe full of free charged particles is especially effective at scattering radiation. The early cosmos was therefore not dark in the simple sense. It was more like a brilliant curtain that had not yet become clear. This also shows why forming atomic nuclei was not enough. Hydrogen nuclei and helium nuclei existed, but they were still bare nuclei, not complete neutral atoms. The electrons were not yet settled into stable atomic arrangements. The universe was still too hot. Whenever an electron tried to join a nucleus, energetic photons could knock it loose again. Matter could not yet relax into the quieter structure of atoms. The ingredients were present, but the temperature kept them from staying assembled. As expansion continued, however, the universe kept cooling. That cooling changed everything. Eventually conditions would become gentle enough for electrons to combine with nuclei and remain attached. Hydrogen nuclei could capture electrons and become neutral hydrogen atoms. Helium nuclei could become neutral helium atoms. This transition would reduce the number of free electrons dramatically, and with fewer free electrons available, photons would finally stop scattering so constantly. That moment would transform the universe. Light would begin to travel freely across space. The glowing plasma would give way to a transparent cosmos. The ancient radiation released then would stretch with the expansion of the universe for billions of years, cooling into the faint microwave glow that astronomers can still detect today. But before that great clearing, the universe remained opaque, luminous, and closed to long-distance light. So the universe before stars was not simply dark from the beginning. It first passed through a time when it was too bright to see through. Light filled it, but could not cross it cleanly. Photons were everywhere, yet always being turned aside by free electrons. The cosmos was glowing, but hidden behind its own heat. Only when expansion cooled that plasma enough for neutral atoms to form could light finally loosen from matter and begin its long, quiet journey across space. For a long time, the young universe was filled with light that could not properly escape. Photons were everywhere, but they were tangled in the glowing plasma, constantly scattered by free electrons before they could travel very far. The cosmos was bright, hot, and opaque, like a lantern hidden inside its own mist. But expansion was quietly changing the conditions. Space kept stretching, temperatures kept falling, and eventually the universe cooled enough for one of the most important transitions in cosmic history. This transition is called recombination, although the name is slightly misleading. It sounds as though electrons and atomic nuclei had been joined together before, then separated, and were now combining again. But in the early universe, this was really the first widespread formation of neutral atoms. The word has stayed because scientists can be deeply attached to old terminology, rather like people who keep mysterious cables in drawers because they might be useful one day. In this case, recombination means the period when free electrons finally joined with atomic nuclei and stayed there. Before this, the universe already contained hydrogen nuclei and helium nuclei. A hydrogen nucleus was usually just a single proton. A helium nucleus contained 2 protons and usually 2 neutrons, but these nuclei were bare, surrounded by a sea of unattached electrons. The universe was still too hot for electrons to remain calmly bound to nuclei. Energetic photons kept knocking them loose, so matter could not yet settle into neutral atomic form. As the temperature dropped, that changed. Electrons began attaching to hydrogen and helium nuclei without being immediately torn away again. Neutral hydrogen atoms formed. Neutral helium atoms formed. The charged particle fog began to clear. Free electrons, which had once been scattered throughout the cosmos in enormous numbers, became far less common. And that made all the difference for light. Photons had been repeatedly redirected by Thomson scattering, the interaction between light and free electrons. But once many electrons became bound inside neutral atoms, there were fewer loose electrons available to scatter photons constantly. Light was no longer trapped in the same restless dance. It could travel. For the first time, photons could move across vast distances without being immediately turned aside. The universe became transparent. This did not mean stars had appeared. There were still no stars, no galaxies, no familiar night sky. But it did mean that light from this moment could begin a journey that would last for billions of years. That ancient light is still detectable today. It is known as the cosmic microwave background, the cooled and stretched afterglow of the early universe. When this light first broke free, it would not have been microwave radiation in the way instruments detect it now. It was far hotter, more like a warm glow filling all of space. But as the universe expanded, the wavelengths of that light were stretched. Expansion made the universe larger, and as space stretched, the light travelling through it stretched as well. Over billions of years, that ancient glow cooled until it became microwave light, faint and nearly uniform across the sky. The cosmic microwave background is one of the strongest pieces of evidence for the Big Bang model. It is not a guess or a poetic metaphor, or the universe leaving a politely labelled note saying, yes, something hot happened earlier. It is real radiation, observed in every direction, carrying information from when the universe first became transparent. It is often described as a baby picture of the universe, though perhaps an unusually blurry baby picture taken when the baby was already about 380,000 years old. The story of its discovery is wonderfully human. In 1965, Arno Penzias and Robert Wilson detected a persistent background noise using a radio antenna in New Jersey. At first, the signal seemed like an unwanted nuisance. They checked the equipment. They considered possible sources of interference. They even dealt with pigeon droppings in the antenna, which is a useful reminder that great scientific discoveries sometimes involve less glamour than expected. But the signal remained. It was coming from every direction. They had detected the cosmic microwave background. This discovery connected beautifully with earlier predictions. George Gamow, Ralph Alpha, and Robert Herman had worked on the physics of the hot early universe and had predicted that leftover radiation should still exist, cooled by cosmic expansion. Their work showed that if the universe had once been hot and dense, it should have left behind an afterglow. Penzias and Wilson found that afterglow by accident, while other scientists nearby were already thinking deeply about how to detect it. Science often advances through theory, patience, clever instruments, and the occasional stubborn hiss that refuses to go away. Later missions studied the cosmic microwave background in much greater detail. The Cosmic Background Explorer measured its spectrum and confirmed that it matched the expected pattern of radiation from a hot early universe with extraordinary precision. The Wilkinson Microwave Anisotropy Probe mapped tiny temperature differences across the sky, revealing subtle variations that correspond to the early seeds of cosmic structure. The Planck Space Observatory measured those variations with even finer detail, helping scientists refine estimates of the universe's age, composition, and large-scale behavior. These tiny differences in the cosmic microwave background matter enormously. The glow is almost the same everywhere, but not perfectly the same. Some regions were minutely warmer or cooler, reflecting slight differences in density. Those tiny irregularities would later be amplified by gravity. Over immense stretches of time, slightly denser regions would draw in more matter, becoming the beginnings of galaxies and clusters. So the cosmic microwave background is not just an old glow, it is a map of early possibility. Yet after this light was released, the universe entered a quieter phase. The glow continued travelling, but expansion stretched it into longer and longer wavelengths. Visible brightness faded. There were still no stars to replace it, no new lamps burning in the dark. Matter was now mostly neutral hydrogen and helium, spread through space with dark matter shaping the invisible gravitational landscape. The universe had become transparent, but not yet luminous in the familiar way. That is the strange beauty of this moment. Light was finally free, and yet darkness was coming. The universe had cleared enough for photons to travel, but not enough for stars to shine. The ancient plasma had released its last great glow, and that glow would slowly cool into the faint microwave whisper still detectable today. After the first atoms formed, the cosmos became open, quiet, and dark, waiting for gravity to gather the gas into the first places where starlight could begin. After the first atoms formed, and the ancient glow of the early universe began travelling freely, the cosmos entered one of its quietest and most mysterious eras. Light had been released, but no stars had yet appeared to replace it. The universe was transparent, but not yet filled with the familiar points of brightness that now define the night sky. This long interval is known as the Cosmic Dark Ages. The name sounds dramatic, almost as though the universe had misplaced the candles and was too embarrassed to mention it. But in scientific terms, the cosmic dark ages simply describe the period after the cosmic microwave background was released, and before the first stars and galaxies began producing new visible light. The universe was no longer a hot opaque plasma. It had cooled enough for electrons and nuclei to form neutral atoms. Photons from the earlier glow could now move through space. But as that ancient light stretched into longer wavelengths with cosmic expansion, visible brightness faded away. There were still no stars. There were no galaxies shining across the dark. The universe had become open but dim. This darkness did not mean emptiness. That point matters, because the word dark can easily give the wrong impression. The universe during this era was not a silent box of nothing. It was filled mainly with neutral hydrogen and helium, the simple atoms formed after recombination. It also contained dark matter, an unseen form of matter whose presence is known through gravity. Photons from the early universe were still travelling, but their wavelengths were being stretched by expanding space. And throughout this vast, cooling sea of matter and radiation, there were tiny density variations, slight unevennesses inherited from the early universe. Those density variations were small, but they were not trivial. They were the places where gravity could begin to make a difference. A region that was slightly denser than average had slightly more gravitational pull. It could attract nearby matter a little more strongly. As it gathered more matter, its pull grew stronger still. This is a slow process, especially at first, but it is one of the most important processes in the entire history of the universe. The Dark Ages were not an interval where nothing happened. They were the time when the first large-scale structure began to gather itself from tiny beginnings. At the same time, the universe continued expanding. Expansion cooled the gas, lowered the background temperature, and stretched the ancient light into longer and longer wavelengths. The cosmos was becoming colder and darker in the ordinary visual sense, but gravity was quietly moving in the opposite direction. While expansion spread the universe out overall, gravity worked locally to pull matter into denser regions. These two processes did not cancel each other neatly. Instead, they shaped the next stage of cosmic history together. Expansion set the broad background. Gravity began choosing where structure would grow. This is one of the reasons the cosmic dark ages are so important. They sit between the first freely travelling light and the first starlight. On one side is the cosmic microwave background, a faint ancient glow from when the universe became transparent. On the other side is cosmic dawn, when the first stars and galaxies began to shine. Between them lies a hidden age of neutral gas, dark matter, cooling space, and growing gravitational structure. It is a bridge made mostly of darkness. It is also difficult to observe directly. During the cosmic dark ages, there were no bright stars or galaxies lighting the universe. Astronomers cannot simply point a telescope and see glowing objects from much of this era, because the bright objects had not formed yet. The main ordinary matter was neutral hydrogen. A neutral hydrogen does not shine like a star. It can absorb or emit radiation in particular ways, but those signals are faint, stretched by cosmic expansion, and buried beneath nearer sources of radio noise. Studying this period is therefore a little like trying to hear a whisper from the early universe while standing beside a modern city full of radios, satellites, electronics, and one neighbour who has decided the lawn needs attention at exactly the wrong moment. One of the most important tools for studying early neutral hydrogen is called the 21 centimetre hydrogen line. This signal comes from a subtle change in the internal energy state of neutral hydrogen atoms. When the electron and proton in a hydrogen atom shift between two slightly different alignments, the atom can emit or absorb radiation with a characteristic wavelength of about 21 centimeters. In the nearby universe, This signal has been used to map hydrogen gas in and around galaxies. For the early universe, it offers something even more ambitious, a possible way to trace neutral hydrogen before and during the era when the first stars began to change it. Because the universe has expanded, ancient 21-centimeter radiation from the cosmic dark ages would be stretched to much longer wavelengths by the time it reached us. That places it in low-frequency radio signals, which are challenging to detect from Earth. Earth's atmosphere, human technology, and natural foreground radiation from our own galaxy all complicate the search. Still, the idea is powerful. If scientists can measure this signal clearly, it could provide a kind of three-dimensional map of neutral hydrogen across cosmic time, showing how the Dark Ages gave way to the first luminous structures. The phrase cosmic Dark Ages, then, should not be understood as a pause in the universe's story. It was more like the quietest part of a deep breath. The glare of the early universe had faded. The first stars had not yet ignited. But beneath the darkness, matter was moving into place. Neutral hydrogen and helium filled space. Dark matter shaped invisible wells of gravity. Slightly denser regions slowly became more significant. The universe was preparing, not consciously, not hurriedly, but through the steady action of physical laws. This preparation would eventually lead to the first cosmic architecture. Dark matter would gather into halos. Gas would fall into them. Some regions would become dense enough and cool enough for collapse to continue. From that collapse, the first stars would eventually form, ending the deepest darkness the universe had ever known. But before the first light of stars, there was this long, shadowed interval, transparent yet dim, simple yet active, quiet yet essential. The cosmic Dark Ages were not the absence of a story. They were the place where the next story was being assembled. During the cosmic Dark Ages, the universe seemed empty of visible structure. There were no bright galaxies, no star clusters, no shining nebulae, and no familiar constellations. But the visible part of the story was not the whole story. Beneath the darkness, something invisible was already shaping the future. The universe was beginning to build around dark matter. Dark matter is one of the most important and most mysterious ingredients in modern cosmology. It is called dark, not because it is necessarily black like soot or shadow, but because it does not emit, absorb, or reflect light in any ordinary detectable way. It does not shine. It does not block light like a solid object. It does not glow in radio waves, visible light, ultraviolet light, or X-rays in the way ordinary matter can. Scientists infer its existence mainly through gravity. Something unseen is pulling on galaxies, shaping galaxy clusters, bending light through gravitational lensing, and influencing the large-scale structure of the universe. This makes dark matter slightly awkward to describe, because it is known by what it does rather than by what it looks like. Ordinary matter is easier. Hydrogen can emit light. Dust can block light. Stars very much announce themselves, sometimes with the subtlety of a lighthouse in a dark room. Dark matter is different. It leaves gravitational fingerprints. It affects motion and structure, yet does not reveal itself through ordinary light. It is one of those cosmic guests that rearranges the furniture but refuses to appear in the photograph. Before stars formed, dark matter was especially important. Ordinary matter, the matter made of protons, neutrons, and electrons, had spent the early universe interacting strongly with radiation. Before recombination, photons and ordinary matter were tightly coupled, and that made it difficult for ordinary matter to clump freely into large structures. Radiation pressure resisted collapse. Dark matter, however, did not interact with light in the same way. It could begin responding to gravity earlier, gathering into slightly denser regions while ordinary matter was still held back by its relationship with radiation. This gave dark matter a head start. Tiny early density variations grew slowly under gravity, and dark matter began forming an invisible scaffolding across the universe. These growing concentrations are called dark matter halos. A halo is not a bright ring or glowing outline in this context. It is a region where dark matter has gathered densely enough to create a gravitational well. Ordinary gas, mostly hydrogen and helium, could later fall into these wells. In a very real sense, the visible universe grew around an invisible framework. The leading cosmological model that describes this broad picture is called the lambda cold dark matter model. It is the standard model of modern cosmology, and it combines several major ingredients: ordinary matter, dark energy, and expanding space. Lambda refers to the cosmological constant associated with dark energy and the accelerated expansion of the universe. Cold dark matter refers to dark matter that moves relatively slowly compared with the speed of light, allowing it to clump effectively and help build cosmic structure. The model does not answer every question, especially the question of what dark matter actually is, but it does a remarkably good job describing many observations of the universe. One of the reasons scientists take dark matter seriously comes from the motion of galaxies. Vera Rubin, working in the 20th century, provided crucial observational evidence through studies of galaxy rotation curves. She found that stars far from the centers of spiral galaxies were moving faster than expected if only the visible matter were present. In simple terms, the outer parts of galaxies behaved as though there was much more mass there than telescopes could see. Rubin's work came billions of years after the cosmic dark ages, of course, and she was not observing the first dark matter halos directly, but her evidence helped show that unseen mass is not a decorative optional extra in cosmology. It is central to how galaxies behave. Dark matter also appears in other lines of evidence. Galaxy clusters contain more gravitational mass than their visible matter suggests. Light from distant objects can be bent by massive foreground structures through gravitational lensing, revealing mass whether or not that mass shines. The cosmic microwave background also carries evidence of the universe's contents. The Planck collaboration, using measurements from the Planck Space Observatory, refined estimates of how much of the universe is made of ordinary matter, and dark energy. These measurements support a universe in which dark matter outweighs ordinary matter by a significant margin. That proportion matters deeply for the story before stars. Ordinary matter was the stuff that would eventually make stars, planets, and people. But dark matter provided much of the gravitational architecture that allowed ordinary matter to gather in the first place. Hydrogen and helium gas did not simply decide one afternoon to become stars, perhaps after a motivational talk from gravity. Gas needed places to collect. Dark matter halos supplied those places. As the universe expanded and cooled, ordinary gas began falling into the gravitational wells created by dark matter. The gas did not instantly become stars. It had to gather, heat, cool, fragment, and collapse further. But without the deeper gravitational pull of dark matter halos, the first star-forming clouds would have been much harder to assemble. Dark matter did not shine, but it helped create the conditions under which shining objects could eventually exist. This is one of the most beautiful reversals in the early universe. The first lights depended on something that did not give off light. Before stars, before galaxies, before the first luminous structures, gravity was already working through an invisible substance. Dark matter gathered first, sketching the outlines of future structure. Ordinary matter followed, falling into those unseen wells, collecting in places where the first stars could eventually ignite. So the universe before stars was not a smooth emptiness waiting for light to appear at random. It had an invisible skeleton, dark matter. Halos formed the first gravitational framework. Hydrogen and helium gas began to gather around it. The future visible universe, with all its galaxies and glowing complexity, was taking shape around something no eye could see. Darkness was not merely the absence of light. It was the setting in which the architecture of light was being built. The first structures in the universe did not appear all at once. There was no sudden moment when darkness neatly folded itself into galaxies, as if the cosmos had finally remembered where it left the instruction manual. Instead, structure began with tiny differences. A little more matter here, a little less matter there. Small variations in density, almost unimaginably subtle at first, became the starting points for everything that would later shine. The early universe was extremely smooth overall. The cosmic microwave background shows this beautifully. Its temperature is almost the same in every direction, a sign that the young universe was remarkably even on large scales. But almost smooth is not the same as perfectly smooth. Hidden in that ancient glow are tiny temperature differences, linked to tiny density differences in the early cosmos. These slight unevennesses were small, but gravity does not need much of an invitation. Given enough time, even a modest difference can become important. This process is called gravitational instability. The basic idea is simple, but powerful. A region that is slightly denser than its surroundings has slightly more gravity. Because it has slightly more gravity, it attracts nearby matter a little more strongly. As it pulls in more matter, it becomes denser still. As it becomes denser, its gravity grows stronger. The effect feeds itself. A small irregularity can slowly become a larger one, not because the universe is in a hurry, but because gravity is persistent. Gravity is not dramatic in the early stages. It does not leap onto the scene wearing a cape. It simply keeps pulling. This is how the universe began turning smoothness into structure. The first tiny variations were not stars, not galaxies, and not even clouds in the familiar sense. They were small differences in how matter and energy were distributed. But over cosmic time, those differences deepened. Dark matter gathered first into invisible halos, and ordinary matter began to respond to those gravitational wells. Hydrogen and helium, the simplest atoms formed after a combination, slowly drifted into regions where gravity was already a little stronger. The challenge was that matter does not collapse just because gravity asks nicely. Gas has pressure. Gas pressure is the outward resistance created by moving particles. When particles in a gas are hot, they move quickly, bumping and spreading outward. This motion pushes against collapse. Gravity pulls inward, trying to gather matter together. Pressure pushes outward, trying to keep the gas spread out. The story of star formation begins with this quiet contest between inward gravity and outward pressure. A classic concept used to understand this balance is the Jeans instability, named after the British physicist James Jeans. The Jeans instability describes when a cloud of gas becomes unstable to gravitational collapse. If gravity is strong enough, and if the cloud is massive or cool enough, the inward pull can overcome the pressure resisting it. If pressure remains too strong, the cloud does not collapse. It may wobble, spread, or settle into a temporary balance. In simple terms, a gas cloud must be heavy enough, dense enough, or cool enough for gravity to win. This idea matters because the early universe was not filled with neat little star seeds ready to switch on. It was filled mostly with hydrogen and helium gas, gently falling into the first small dark matter halos. These halos acted like invisible basins in the landscape of gravity. Gas collected inside them, but collection alone was not enough. As gas fell inward, it gained energy and heated up. Hotter gas created more pressure. That pressure resisted further collapse, so gravity faced a problem. It could gather the gas, but keep collapsing toward the dense conditions needed for stars. The gas had to lose energy. This is where cooling becomes essential. Matter cannot simply collapse forever unless it can shed energy. When gas loses energy, its particles move more slowly. The pressure drops. With less pressure pushing outward, gravity can pull the gas into smaller and denser regions. Cooling allows collapse to continue. Without cooling, the gas can become trapped in a warm, puffed-up state, gathered by gravity but unable to shrink enough to form stars. In the later universe, cooling can happen through many channels. Gas containing heavier elements can radiate energy efficiently. Dust grains can help. Complex chemistry can make collapse easier. But before the first stars, the universe had almost none of those helpful ingredients. There was mostly hydrogen and helium, with tiny traces of lithium. No carbon-rich dust. No oxygen-bearing molecules in useful amounts. No metals in the astronomical sense, meaning elements heavier than hydrogen and helium. The first star-forming gas had to work with a very limited toolkit. It was rather like trying to build a cathedral with 2 kinds of brick and a great deal of optimism. Still, the process began. Hydrogen and helium gathered into small dark matter halos. Slightly denser regions became denser still. Gravity amplified the early irregularities. Gas fell inward, heated, resisted, cooled where it could, and continued to collect. The first clouds were not yet stars, but they were the places where stars became possible. They were the universe's first nurseries, though still dark, primitive, and chemically simple. This slow gathering is one of the most important transitions in cosmic history. Before it, the universe had matter but no luminous structure. It had atoms but no stars. It had invisible dark matter, halos, but no glowing galaxies. Gravitational instability turned tiny early differences into the beginnings of architecture. The gene's instability helps explain when gas could cross the threshold from merely gathering to actually collapsing. Gas pressure explains why collapse was not automatic. Cooling explains why gravity needed help. So in the long darkness before the first stars, the universe was learning how to gather. Not consciously, not quickly, and not with any grand announcement. Hydrogen and helium drifted into invisible wells. Density grew from slight unevenness. Gravity pulled. Pressure resisted. Cooling quietly tipped the balance. And in those first small halos, long before the sky had any stars to offer, the conditions for the first stellar fires were being assembled. As gravity gathered hydrogen and helium into the first dark matter halos, the universe faced a quiet but serious problem. It was not enough for gas to fall inward. It was not enough for matter to become denser. To make the first stars, the gas had to keep collapsing until its central regions became hot and compressed enough for nuclear fusion to begin. And for that to happen, the gas needed to lose energy. It needed to cool. That may seem backwards at first. Stars are hot after all. They're enormous glowing spheres of plasma powered by nuclear fusion in their cores. So it might sound odd to say that cooling was needed before stars could form, but collapsing gas behaves in a particular way. As gas falls inward under gravity, it gains energy. Particles move faster, collisions become more frequent, temperature rises, and as the gas heats up, its pressure increases. That pressure pushes outward, resisting further collapse. Without some way to shed energy, the gas can become stuck, gathered, compressed, warmer than before, but not yet able to shrink into a true stellar core. Cooling allows gravity to continue its work. When gas radiates energy away, its particles move less violently. Pressure weakens. The cloud can contract further. As it contracts, it may heat again, then cool again, then contract again. Star formation depends on this long negotiation between gravity pulling inward and pressure pushing outward. Gravity supplies the ambition. Cooling supplies the permission. In the modern universe, gas clouds have many ways to cool. They can contain heavier elements such as carbon, oxygen, silicon, and iron. They can contain dust grains, tiny solid particles that absorb and emit radiation. They can contain molecules that radiate energy through rotations and vibrations. This makes modern star formation, while still complex, much easier than it was at the beginning. The universe today has had billions of years of stellar recycling. Earlier generations of stars have enriched space with heavy elements, and that enrichment gives later gas clouds more efficient ways to lose heat. The first star-forming clouds had no such luxury. They were chemically simple, almost dramatically so. They contained mostly hydrogen and helium, the elements produced in the early universe, along with only tiny traces of lithium. There was almost no carbon, almost no oxygen, no useful supply of silicate dust grains, no rich molecular chemistry of the kind found in modern interstellar clouds. The first clouds had to make stars from a very plain cosmic pantry. Hydrogen and helium were abundant, but they were not especially good at cooling gas to the very low temperatures needed for easy fragmentation and collapse. Ordinary atomic hydrogen can radiate energy under certain conditions, but in the first small star-forming halos, it could not cool the gas far enough on its own. This mattered, because cooler gas can collapse into smaller, denser clumps. Hotter gas resists collapse more strongly and tends to form larger structures. Without an efficient coolant, the first stars were expected to form differently from many stars today. The gas remained warmer, the collapsing clumps were larger, and the stars that eventually emerged may often have been far more massive than the Sun. The key cooling agent in those first clouds was molecular hydrogen. Molecular hydrogen forms when two hydrogen atoms join together into a simple molecule. It is just about the most basic molecule the universe can make, a tiny partnership between the two most common atoms in existence. It is not flashy. It does not sound like the sort of thing that should change cosmic history, but in the early universe, even a small amount of molecular hydrogen mattered enormously. Molecular hydrogen could radiate energy away from gas clouds more effectively than plain atomic hydrogen under those early conditions. It did this through changes in its internal motion, allowing the gas to lose some of the energy that would otherwise keep it too warm and too resistant to collapse. The effect was limited because molecular hydrogen is not as efficient a coolant as the heavier elements and dust available later, but it was enough to open a pathway. It allowed the first gas clouds to cool from very hot conditions down to lower temperatures, helping gravity pull material into denser central regions. This was not an easy process. Molecular hydrogen itself had to form in a universe with very few ingredients. Because the first gas contained almost no dust grains, it lacked one of the important surfaces that helps molecules form in modern interstellar clouds. Instead, molecular hydrogen had to form through slower gas phase reactions involving particles such as free electrons and hydrogen ions. The details are subtle, but the main point is simple. The first chemistry of star formation was sparse, delicate, and crucial. The universe needed just enough molecular hydrogen to let gas radiate away heat and continue collapsing. Later stars formed under richer conditions. Once the first generations of stars lived and died, they spread heavier elements into surrounding space. Carbon, oxygen, silicon, iron, and dust grains changed everything. They allowed gas clouds to cool more efficiently, fragment into smaller pieces, and form stars with a wider range of masses. The later universe became a better star-making environment because stars themselves had improved the ingredients. It is a wonderfully circular piece of cosmic logic. Stars made the universe better at making stars, very considerate of them eventually. But the first stars had no earlier stars to help them. They formed from pristine gas, meaning gas almost untouched by heavy elements. These first stars are known as population 3 stars. The name does not mean they were third in time. Astronomers use population 1 for relatively metal-rich stars like the Sun, population 2 for older, metal-poor stars, and population 3 for the earliest, nearly metal-free stars. The numbering is a little counterintuitive, as though the universe filed its paperwork in reverse, but the meaning is clear enough once explained. Population 3 stars were born from the cooling problem. Their existence depended on whether hydrogen and helium gas could gather inside dark matter halos, form enough molecular hydrogen, lose enough heat, and collapse deeply enough for nuclear fusion to ignite. This was a delicate physical pathway from diffuse gas to the first stellar cause. Nothing about it was guaranteed in a simple everyday sense. The universe had to pass through a chain of conditions. Dark matter halos had to form, gas had to fall in, molecular hydrogen had to cool it, and gravity had to compress it further. So before the first stars shone, the universe had to solve a quiet thermal puzzle. Gravity could gather matter, but heat pushed back. Hydrogen and helium were abundant, but poor at cooling on their own. Molecular hydrogen, fragile and modest, became the essential helper. It allowed the first star-forming clouds to radiate energy, shrink more deeply, and move toward the temperatures and densities required for stellar birth. In the long darkness, this was one of the most important hidden transitions. The universe was not only gathering matter, it was learning how to lose heat. And once enough gas could cool inside the first dark matter halos, the path toward the first stars finally became possible. The darkness had not ended yet, but somewhere within it, the first stellar fires were beginning to find the conditions they needed. Deep inside the first small dark matter halos, where hydrogen and helium had gathered through long ages of quiet collapse, the universe approached a threshold it had never crossed before. Until now, there had been matter, radiation, dark matter, gravity, cooling, and darkness. There had been nuclei, atoms, and simple molecules, but there had not yet been stars. No object had yet ignited with sustained nuclear fusion. No stellar surface had yet poured fresh light into the surrounding gas. The cosmos had prepared the ingredients, shaped the invisible wells, and solved just enough of the cooling problem. Now, at last, the first stars could begin to form. These first stars are known as population 3 stars. They are called hypothetical, not because scientists doubt that the first generation of stars existed, but because no confirmed direct observation of a true population 3 star has yet been made. Their existence follows naturally from the broader story of cosmic evolution. The universe once had no stars. Later, it had stars. Therefore, at some point, a first generation had to appear. But finding one directly is extremely difficult, because they would have formed very early, lived long ago, and may have died quickly. Astronomers are still searching for their direct signatures, making them one of the important missing pieces in observational cosmology. Population 3 stars would have formed from nearly pristine material. Pristine, in this context, means gas that had not yet been enriched by previous generations of stars. It was made mostly of hydrogen and helium, with only tiny traces of lithium left from Big Bang nucleosynthesis. There was essentially no carbon, oxygen, silicon, iron, or dust, in the way later star-forming clouds would have them. The universe had not yet produced those heavier ingredients in meaningful amounts. They would come later, from stars themselves. Astronomers often use the word metals in a special way. In everyday language, a metal might mean iron, copper, gold, or something that makes a satisfying clink when dropped, preferably not onto a toe. In astronomy, metals means all elements heavier than hydrogen and helium. Carbon is counted as a metal, oxygen is counted as a metal, Neon, magnesium, silicon, and iron are all metals in this astronomical sense. So when scientists say population 3 stars were metal-free, they do not mean the stars were missing shiny hardware. They mean these stars formed before the universe contain significant amounts of elements heavier than hydrogen and helium. That lack of metals mattered because heavier elements and dust grains help gas cool efficiently. In later cosmic history, metal-rich gas clouds could lose heat in many ways. They could fragment into smaller clumps, forming stars of many different masses, including small, long-lived stars like red dwarfs. But the first gas clouds were much simpler. Molecular hydrogen helped them cool, but not as effectively as heavy elements and dust would later do. As a result, the gas likely stayed warmer while collapsing. Warmer gas has more pressure, and pressure resists breaking into small fragments. This is one reason many models suggest that the first stars were often very massive compared with many stars today. The exact masses of population 3 stars remain uncertain. Earlier models often suggested extremely massive stars, perhaps hundreds of times the mass of the Sun. More recent simulations show a more complicated picture, where some may have been less massive, depending on how the gas fragmented, how rotation shaped the collapse, how radiation affected the surroundings, and how material flowed onto the growing star. But the broad expectation remains that the first stars were generally heavier than typical stars forming in the modern universe. They were born in a simpler, warmer, more primitive environment. The path from a dark gas cloud to a star began with gravitational collapse. Hydrogen and helium gas collected inside a dark matter halo. Molecular hydrogen allowed some of that gas to lose heat and contract further. As the central region became denser, gravity pulled it inward more strongly. The gas fell toward the middle, compressed and heated. Eventually, a dense protostellar core formed. A protostar is not yet a full star in the stable, long-lived sense. It is a growing object, still gathering mass from the surrounding gas, becoming hotter and denser as gravity squeezes it inward. This collapse raised both temperature and pressure. At first, the heating came from gravitational energy. As gas fell inward, its energy of motion increased, and collisions between particles turned that motion into heat. The deeper the collapse went, the hotter the central region became. But to become a true star, the core had to reach conditions where nuclear fusion could begin. Nuclear fusion is the process that powers stars. In simple terms, it occurs when lighter atomic nuclei combine to form heavier nuclei, releasing energy. In stars like the Sun, hydrogen nuclei ultimately combine into helium through a chain of reactions. That released energy creates the pressure that helps support a star against its own gravity and produces the light and heat that flow outward. For the first stars, once fusion ignited in their cores, the universe gained something entirely new: sustained stellar light. This was not merely a lamp switching on, it was a profound physical transformation. A star is a balancing act between gravity and internal pressure. Gravity pulls inward, trying to compress the star. Fusion in the core releases energy, creating pressure that pushes outward. When those forces settle into balance, a star can shine steadily for as long as its fuel and structure allow. For massive population 3 stars, that lifetime may have been short by stellar standards, perhaps only a few million years. But even a few million years was enough to change the young universe around them. The first starlight would have been intense. Massive hot stars produce large amounts of ultraviolet radiation. This radiation could heat nearby gas, break apart molecules, and begin ionizing hydrogen by stripping electrons away from atoms. The first stars, therefore, did not simply shine politely into the darkness. They changed the chemistry and temperature of their surroundings. They began turning the cosmic dark ages into cosmic dawn. Still, the first stars remain difficult to see directly. They formed so far away and so early that their light has been stretched by the expansion of the universe for more than 13 billion years. If any direct signal from them reaches modern telescopes, it arrives faint, red-shifted, and mixed with the light of later objects. Observatories such as the James Webb Space Telescope are helping scientists study very early galaxies and possible indirect evidence of the first stellar generations, but a confirmed direct observation of an individual true population 3 star has not yet been made. So the first stars live partly in theory, simulation, and indirect evidence. They are predicted by cosmology, shaped by physics, and pursued by observation. They represent the missing bridge between a universe filled with simple gas and a universe rich with light, heavy elements, galaxies, and planets. When population 3 stars began to form, the deepest darkness of the universe started to end. Not everywhere at once, not suddenly across all of space. The first starlight would have appeared in isolated regions, inside small halos where gas had collapsed far enough to ignite. Around each new star, the darkness changed. Hydrogen was heated, atoms were ionized, radiation spread outward. The first stellar cores became the first engines of cosmic transformation. Before them, the universe had been transparent but dim. After them, it began to shine from within. The first stars were made from the simplest ingredients, but they opened the path to everything more complex. In their light, the universe began moving from darkness toward structure, from simple atoms toward heavy elements, from silent gas toward galaxies. And somewhere in that ancient, unreachable dawn, the first star began to burn. The first stars were not gentle little suns quietly taking their place in a mature galaxy. They were born into a universe that had never hosted starlight before, from gas that was almost entirely hydrogen and helium, with only tiny traces of lithium. They had no older stellar neighbours to inherit from, no heavy elements to help shape their formation, and no dust-rich clouds like the ones that help stars form today. They were the first attempt the universe made at building stars, and the result was probably very different from the calm yellow star that lights Earth. Population 3 stars are expected to have been massive, hot, bright, and short-lived. Not every detail is known, because no confirmed direct observation of a true population 3 star has yet been made. But theory and numerical simulations suggest that many of them may have contained tens, perhaps hundreds, of times the mass of the Sun. Some models allow for a range of masses, so it would be too simple to imagine them all as identical cosmic giants. Still, compared with many stars in the modern universe, the first stars were likely weighted toward the large and powerful end of the stellar family. The reason comes back to cooling. The first star-forming gas had almost no heavy elements. Astronomers use the word metals for all elements heavier than hydrogen and helium, even when those elements are not metals in everyday language. Carbon, oxygen, and nitrogen all count as metals in astronomy. So, when these early stars are described as metal-free, it means they formed before the universe had been meaningfully enriched with heavier elements. Without those heavier elements, and without dust grains, the first gas clouds could not cool as efficiently as later gas clouds. Warmer gas resisted fragmenting into many small pieces. Instead, it tended to gather into larger collapsing clumps, producing stars that may have grown very massive. These stars would probably have looked nothing like the Sun. The Sun is a middle-aged, relatively modest star by mass, made from gas that already contained many heavier elements from earlier generations of stars. Those elements affect opacity, temperature, structure, and the way energy moves through a star. Population 3 stars lacked that chemical richness. Their internal structures would have been shaped by nearly pure hydrogen and helium. With fewer heavy elements to absorb and redistribute radiation, many of these stars may have burned hotter and bluer than the Sun, pouring out intense ultraviolet radiation into the surrounding darkness. That ultraviolet radiation mattered. It was energetic enough to affect the neutral hydrogen that filled the early universe. Around the first stars, ultraviolet photons could heat nearby gas and begin ionizing hydrogen, which means stripping electrons away from hydrogen atoms. This created growing regions of ionized gas around early light sources. At first, these regions were local bubbles in a much larger neutral universe. The transformation did not happen everywhere at once. The first stars lit small patches of cosmic darkness, and those patches began to alter the state of the gas around them. The lives of population 3 stars may have been extremely brief by stellar standards. A star like the Sun can shine for about 10 billion years in its main stable lifetime. Smaller red dwarf stars can last far longer, sometimes for trillions of years. Massive stars, however, live fast. This sounds like a motivational slogan for reckless stars, but it is really physics. A massive star has more fuel, but its core becomes far hotter and denser, so it burns that fuel at a much greater rate. The increase in fuel is more than outweighed by the increase in energy output. Because of this, some of the first massive stars may have lived only a few million years. That is a blink compared with the age of the universe, and even compared with the lifetime of the Sun. Yet during those few million years, they could have had an enormous impact. They shone intensely. They flooded their surroundings with ultraviolet radiation. They pushed on nearby gas with radiation pressure and stellar winds. And when they reached the end of their lives, many may have died in powerful explosions, spreading newly made elements into space. This short lifetime is one of the reasons direct evidence is so difficult to obtain. If population 3 stars were mostly massive, they would have disappeared long ago. They would not still be shining today in nearby galaxies, patiently waiting for astronomers to notice them. Instead, scientists must search for indirect evidence, the chemical fingerprints they left behind, the early galaxies they helped illuminate, the radiation they contributed to cosmic reionization, and perhaps rare distant signals from objects seen when the universe was very young. Theoretical modelling and numerical simulations are essential for studying them. Scientists use supercomputers to model how gas collapsed inside early dark matter halos, how molecular hydrogen cooled that gas, how protostars gathered mass, and how radiation from the forming stars affected their surroundings. These simulations must combine gravity, gas dynamics, radiation, chemistry, and dark matter. It is a difficult task, partly because the physical processes operate across very different scales, from vast cosmic environments down to dense stellar cores. The universe, as usual, does not simplify itself just because people would appreciate a tidier spreadsheet. Different simulations can produce different details. Some suggest that early gas clouds may have fragmented into small groups of stars rather than always forming single enormous stars. Some indicate that radiation from a growing protostar could limit how much mass it ultimately gained. Others explore how rotation, turbulence, and magnetic fields may have influenced the final result. So the picture is not completely settled. The first stars were probably not all the same, and their exact properties remain an active area of research. Still, the broad role of these stars is clear. They were the first stellar furnaces. Inside their cores, nuclear fusion began turning hydrogen into helium, and in later stages of massive stellar evolution, heavier elements could form. The first stars therefore began changing the chemical identity of the universe. Before them, the cosmos was made mostly of hydrogen and helium. After them, tiny amounts of heavier elements began entering space. Carbon, oxygen, silicon, and other elements could start to appear. not everywhere, and not in great abundance at first, but enough to begin the long enrichment of the cosmos. This chemical change was one of the most important consequences of the first stars. Their light helped end the deepest cosmic darkness, but their interiors and deaths prepared the universe for later complexity. Without stars, the universe would have remained chemically simple. With stars, it began to build the ingredients for rocky planets, atmospheres, oceans, and living chemistry. So the first stars were brief, brilliant, and transformative. They were likely massive and intensely hot, shining with hard ultraviolet light into a universe that had never seen stellar fire before. They lived quickly because massive stars spend their fuel extravagantly, like someone who finds a candle and decides the best use for it is to light an entire forest of fireworks. And though their lives were short, their effects were lasting. They heated the gas around them. They began ionizing neutral hydrogen. They produced the first meaningful supply of heavy elements. In their cores and in their endings, the universe began learning how to become chemically rich. The first stars did more than shine. They began changing what the universe was made of. Before them, the cosmos was chemically simple, almost austere. It contained mostly hydrogen and helium, with only tiny traces of lithium. That was enough to build the first stars, but not enough to build rocky planets, oceans, atmospheres, or living chemistry. For those, the universe needed heavier elements, and the first great factories for those heavier elements were stars. The creation of elements inside stars is called stellar nucleosynthesis. Nucleosynthesis means the making of atomic nuclei. In stars, this happens mainly through nuclear fusion, the process where lighter atomic nuclei combine into heavier nuclei and release energy. In the simplest and most familiar example, hydrogen nuclei are fused into helium in stellar cores. This fusion releases the energy that allows a star to shine and resist the inward pull of its own gravity. But in massive stars, the story does not stop with helium. Under the right conditions, stars can build heavier and heavier elements in a sequence of nuclear reactions. This idea was developed through the work of several important scientists. Fred Hoyle was one of the key figures connected to the theory of stellar nucleosynthesis, especially the understanding that stars could manufacture heavier elements. Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle together produced major work explaining how elements are formed in stars. Their work helped transform the way scientists understood cosmic chemistry. The elements were not simply present from the beginning. Many of them had histories. They had birthplaces. They had been forged inside stars. In the first stars, this was especially important because the universe had barely any heavy elements before they formed. Carbon, oxygen, nitrogen, silicon, and iron did not exist in meaningful amounts after the Big Bang. The early universe made mostly hydrogen and helium with a very small amount of lithium. It did not make a rich periodic table. It made the basic fuel, not the finished architecture. The more complex ingredients had to wait for stars to ignite. Inside massive population 3 stars, fusion could proceed through stages. Hydrogen fused into helium. Helium could later contribute to the formation of carbon. In very massive stars, further reactions could create oxygen, neon, magnesium, silicon, sulfur, and other elements. The exact pathways depended on the mass, temperature, pressure, and lifetime of the star. Stellar interiors are not calm little kitchens with labelled jars, though that would make astrophysics easier to decorate. They are extreme environments where gravity compresses matter to enormous densities, and nuclear reactions unfold under temperatures far beyond ordinary experience. Carbon was especially important. It is the backbone of organic chemistry, capable of forming long chains and complex structures. Oxygen mattered too, becoming essential later for water, rocks, atmospheres, and eventually biological respiration on worlds like Earth. Nitrogen would become a key part of proteins and genetic molecules. Silicon would help form rocky minerals. Iron would become central to planetary cores, magnetic fields, and many later astrophysical processes. These elements were not decorative additions to the universe. They were the foundations of complexity. Without stellar nucleosynthesis, the universe might have remained mostly a vast sea of hydrogen and helium. There could be stars, perhaps, but not planets like Earth. There could be gas, but not granite, oceans, clay, rust, or the chemistry of living cells. The familiar world is made from elements that had to be manufactured. The calcium in bones, the oxygen in water, the carbon in every living tissue, and the iron in blood all belong to a cosmic story that began when stars started turning simple nuclei into heavier ones. The first stars did not instantly make the universe rich in heavy elements. That is important. Cosmic enrichment was gradual. The earliest heavy elements were rare, scattered into local regions around the first stars. The universe did not go from chemically simple to chemically rich overnight, as though someone had spilled a box of elements across space and called it progress. It took many generations of stars. Each generation formed from gas, lived, produced new elements, and returned some of that material to space. Later stars then formed from gas that was slightly more enriched than before. This gradual enrichment changed star formation itself. The first stars formed from nearly pristine hydrogen and helium with very poor cooling options. Once even small amounts of heavier elements and dust entered the gas, clouds could cool more efficiently. They could fragment more easily into smaller clumps. That meant later generations of stars could form with a wider range of masses, including smaller stars capable of living for billions of years. Heavy elements did not merely add variety to the universe, they changed how the universe made new stars. But for those elements to matter, beyond the stars that created them, they had to escape. A heavy element locked inside a stellar core cannot become part of a planet, a moon, or a future living cell. It has to be expelled into space. This connects heavy element production directly to stellar death. Massive stars can release newly formed elements through powerful winds and, more dramatically, through supernova explosions. In those deaths, enriched material is thrown outward into surrounding gas, mixing with the interstellar medium and altering the chemistry of future star-forming clouds. For population 3 stars, this stage was crucial. If many of them were very massive, some may have ended in extraordinary explosions, spreading the first meaningful heavy elements into the young universe. Others may have collapsed into black holes, trapping some of their material. The exact outcomes remain an active area of research, but the broad principle is clear. Stars had to live, transform matter in their cores, and then return at least some of that transformed matter to space. The first heavy elements were therefore not just products of stellar interiors. They were messages sent forward. Carbon and oxygen made in early stars could become part of later gas clouds. Those clouds could form new stars. Around some of those stars, planets could eventually assemble. Much later, on at least one small rocky world, atoms made in ancient stars would become oceans, mountains, microbes, trees, and minds capable of tracing the story backward. Before the first stars, the universe had the ingredients for light. After the first stars, it began to gain the ingredients for worlds. Stellar nucleosynthesis turned simple matter into the beginnings of chemistry. It did not complete the process at once, and it did not make the universe rich immediately. But it opened the path. Inside the first stars, hydrogen and helium began a long transformation into the elements that would one day make the universe not only brighter, but more varied, more textured, and finally, in rare places, alive. The first stars were not built to last quietly for billions of years. Many of them were probably massive, hot, intense, and brief. They formed from simple gas, burned through their fuel at extraordinary rates, and then, in many cases, ended violently. Their deaths were not just dramatic finales. They were one of the great turning points in cosmic history, because they helped spread the first heavy elements into surrounding space. A massive star spends its life in a long struggle between gravity and pressure. Gravity pulls inward, trying to crush the star under its own weight. Fusion in the core releases energy, creating outward pressure that holds the star up. For a while, the balance can be stable. Hydrogen fuses into helium. Later, in very massive stars, helium and heavier nuclei can take part in further fusion stages, building elements such as carbon, oxygen, neon, magnesium, silicon, and eventually iron. But this process cannot continue forever. Iron is a kind of ending point for ordinary stellar fusion in massive stars. Fusing iron into heavier elements does not release energy in the same helpful way that earlier fusion reactions do. Once a massive star builds up an iron-rich core, the core can no longer support itself through energy-producing fusion. Gravity begins to win. The core collapses inward with astonishing force, and the outer layers can be blasted away in a core collapse supernova. A core collapse supernova is the death of a massive star whose central regions can no longer resist gravity. The collapse is sudden, extreme, and physically complex. Matter in the core is compressed to extraordinary densities. In many cases, the result left behind may be a neutron star, an incredibly dense remnant made largely of neutrons. In other cases, if the collapsing core is massive enough, it may form a black hole. Meanwhile, the outer layers of the star are thrown into space, carrying newly made elements out into the surrounding gas. For the earlier stars, this was especially important. Before them, the universe was made mostly of hydrogen and helium, with only traces of lithium. Inside them, heavier elements began to form, but those elements could not help build later stars or planets while locked inside stellar interiors. Supernovae provided a way to scatter them outward. The death of a star became a kind of cosmic delivery system, though admittedly one with rather more explosion than most delivery services recommend. Some extremely massive first stars may have ended in an even more unusual way through a process called pair instability supernovae. In a very massive star, the core can become so hot that high-energy radiation produces pairs of particles and antiparticles, especially electrons and positrons. This process removes some of the radiation pressure that had been helping support the star against gravity. With less pressure, the core contracts. The contraction heats the core further, triggering runaway nuclear burning. In some cases, the entire star can be blown apart, leaving no compact remnant behind. Pair instability supernovae are especially interesting, because they could spread large amounts of heavy elements into the early universe. They are also predicted to leave distinctive chemical patterns, different from those produced by ordinary core collapse supernovae. Scientists look for hints of these patterns in ancient stars, because a very old star with extremely low metal content may preserve traces of the material from one or a few earlier supernovae. Such stars are not first stars themselves, but they may carry the chemical memory of the stars that came before them. Not every first star necessarily died the same way. Mass mattered, rotation mattered. The way material flowed onto the star during formation mattered. The presence of magnetic fields may have mattered. Some stars may have exploded as core collapse supernovae. Some may have undergone pair instability explosions. Some may have collapsed more quietly into black holes, swallowing much of their heavy element material instead of spreading it widely. The first stellar generation was probably not a single neat category, with one identical ending. Nature rarely behaves like a tidy filing cabinet, especially when stars hundreds of times the mass of the Sun may be involved. These different deaths shape the early universe in different ways. A powerful explosion could heat nearby gas, push material outward, and enrich the surrounding region with heavier elements. That enrichment changed the conditions for later star formation. Even tiny amounts of carbon, oxygen, silicon, and iron could help gas cool more effectively than pristine hydrogen and helium alone. Cooling allowed clouds to fragment into smaller pieces, helping later generations of stars form with a wider range of masses. The first supernova, therefore, did not just add new elements, they helped change the way the universe made stars. The search for evidence continues in the Milky Way and in nearby dwarf galaxies. Astronomers study very old metal-poor stars, looking carefully at the proportions of elements in their atmospheres. These stars can act like fossil records. Their light carries chemical fingerprints of the gas from which they formed. If that gas had been enriched by one of the first supernovae, then the star may preserve clues about the mass and death of an ancient population 3 star. This work connects modern stellar archaeology to events that happened more than 13 billion years ago. Dwarf galaxies are especially useful because some of them have had relatively quiet histories compared with large galaxies like the Milky Way. Their old stars may preserve clearer traces of early chemical enrichment. By comparing observed element patterns with theoretical models of supernova explosions, scientists can test ideas about how the first stars lived and died. The evidence is subtle, and the conclusions are rarely simple, but each ancient star adds another small piece to the puzzle. The first supernovae marked a shift from isolated first stars toward a more complex universe. Their explosions stirred gas, spread heavy elements, and changed the chemistry of future star-forming regions. Around them, the dark universe became more textured. Light had already begun to appear, but now the material foundations of later galaxies were being altered. The first stars did not merely shine and vanish. In dying, they seeded their surroundings with the ingredients of future complexity. From those first explosions, the universe began moving away from chemical simplicity. The gas between stars was no longer perfectly pristine. New elements drifted through early halos. Later stars would form from slightly enriched material. The first galaxies would grow from regions where gravity, gas, light, and heavy elements were beginning to interact. Supernovae were destructive events, but their destruction was also creative. They broke the first stars apart, and in doing so gave the universe new pieces with which to build. The first stars did not appear inside great spiral galaxies like the Milky Way. There were no wide glowing disks, no elegant spiral arms, no calm stellar suburbs arranged around bright galactic centres. The first galaxies were probably much smaller, rougher and more chaotic than the galaxies seen nearby today. They were young systems built from dark matter, gas and early stars, still finding their shape in a universe that had only recently begun to shine. Their formation grew from the same process that had already begun in the darkness. Dark matter gathered into halos. Hydrogen and helium gas fell into those gravitational wells. In some of the densest regions, the first stars formed. Then, over time, small halos merged with other small halos. Gas clouds collided, mixed, heated, cooled, and collapsed again. Early star-forming regions gathered into larger systems. The first galaxies were not created in one neat step. They assembled gradually through the merging and clustering of smaller structures. This process is called hierarchical structure formation. The idea is that smaller cosmic structures formed first, then gradually merged into larger galaxies, galaxy groups, and galaxy clusters. In this picture, the universe did not begin by building giant galaxies fully formed. like grand cosmic mansions appearing on an empty street. It began with smaller clumps of dark matter and gas. These clumps combined over time, creating larger and more complex structures. The largest galaxies grew from many smaller beginnings. The first galaxies were likely irregular and turbulent. They may have looked less like graceful modern spirals and more like bright, uneven knots of young stars and gas. Their shapes would have been disturbed by mergers, bursts of star formation, supernova explosions, and inflowing gas. Some may have contained only a few million stars rather than the hundreds of billions found in a large galaxy like the Milky Way. Others may have been even smaller, more like fragments of future galaxies than mature galaxies themselves. This makes them deeply important. They were the first places where stars began to form in groups rather than in lonely isolation. Within them, gas could be enriched by the deaths of earlier stars, then recycled into new stars. Supernovae stirred their surroundings. Radiation heated and ionized nearby hydrogen. Heavy elements began spreading from star-forming regions into the wider gas. The first galaxies were not just collections of stars. They were the first working ecosystems of cosmic evolution, though admittedly without trees, birds, or anyone complaining about the local weather. Modern astronomers study these early galaxies with powerful observatories, especially the James Webb Space Telescope. The James Webb Space Telescope is operated through a collaboration involving the National Aeronautics and Space Administration, the European Space Agency, and the Canadian Space Agency. Its infrared instruments are especially valuable for studying the distant universe, because the light from the earliest galaxies has been stretched by cosmic expansion. The stretching is called redshift. As the universe expands, the wavelength of light travelling through space is stretched along with it. Light that began as ultraviolet or visible light from a young galaxy can arrive at modern telescopes shifted into infrared wavelengths. The farther away a galaxy is, and the longer its light has travelled through expanding space, the more its light is redshifted. This is why infrared astronomy is so important for studying the early universe. The first galaxies are not simply faint. Their light has been moved into a different part of the spectrum. Observing them is difficult for several reasons. Their light has travelled for more than 13 billion years, so it arrives extremely faint. These galaxies are also seen as they were when the universe was young, not as they would look today. The farther astronomers look, the further back in time they are looking. A very distant galaxy is not just far away in space. It is a preserved image from an ancient stage of cosmic history, carried by light that began its journey before the Earth existed. The expansion of the universe adds another layer of difficulty. Redshift makes early galaxies appear in infrared light, which requires specialized instruments and careful analysis. Dust, foreground galaxies, gravitational lensing, and uncertainties in distance measurements can complicate the picture. Astronomers must work carefully to distinguish truly ancient galaxies from closer objects that may appear similar in some observations. The early universe is generous with clues, but it does not always label them neatly, which feels slightly inconsiderate after 13 billion years of travel. Even so, observations have revealed galaxies from astonishingly early times. The James Webb Space Telescope has found candidates for galaxies that existed only a few 100 million years after the Big Bang, pushing scientists to refine models of how quickly structure formed. Some early galaxies appear brighter or more developed than expected, though interpretation is still ongoing. This does not mean the Big Bang model has collapsed, despite the occasional excited headline trying very hard to make everyone spill their tea. It means the details of early galaxy formation are being tested with better data. The first galaxies changed the universe around them. As more stars formed, more light entered the darkness. Massive stars produced ultraviolet radiation, heating nearby gas and helping ionize hydrogen. Supernovae scattered heavy elements through early galactic environments. gas became less pristine. Star formation became more complex. The universe was moving from isolated first stars toward networks of growing luminous structure. These early galaxies were small, restless places, but they carried the future inside them. Within them were the first cycles of star birth and stellar death, the first repeated enrichment of gas, and the first larger gathering of light. They were the beginning of the universe's visible architecture. From dark matter halos and simple gas, from mergers and turbulence, from hot stars and supernovae, the first galaxies began to take shape. The cosmos was no longer only dark space with rare first lights. It was becoming structured, clustered, and increasingly luminous. The first galaxies marked the moment when starlight stopped being a scattered event and began becoming a cosmic pattern. Around them, darkness was still vast, but it was no longer untouched. Light, heat, radiation, and heavy elements were spreading through the young universe, and the great web of galaxies had begun to grow. The first stars and galaxies didn't merely add light to the universe. They began changing the universe's physical state. Before they appeared, much of ordinary matter between forming structures existed as neutral hydrogen, simple atoms with electrons bound to protons. This neutral hydrogen filled intergalactic space like an ancient cosmic fog, not a fog of droplets, but a widespread sea of atoms able to absorb certain kinds of light. Then the first bright sources began to shine, and the fog slowly started to lift. This era is known as cosmic reionization. The word describes a time when energetic radiation stripped electrons away from neutral hydrogen atoms across vast regions of space. Hydrogen that had once been ionized in the hot early universe became neutral after recombination, when electrons joined with nuclei and the cosmos became transparent. Reionization was the later reversal of that state. The first stars and galaxies began sending out radiation powerful enough to break neutral hydrogen apart again, turning much of the gas between galaxies back into ionized plasma. This did not happen everywhere at once. The universe was far too large, uneven, and complicated for a clean, instant transformation. Reionization probably began in patches, around the earliest bright sources. A young galaxy filled with massive hot stars could produce intense ultraviolet radiation. That radiation spread outward, ionizing the hydrogen nearby and creating a bubble of ionized gas around the galaxy. Elsewhere, farther away from bright sources, hydrogen could remain neutral for longer. The early universe became a patchwork of ionized bubbles and neutral regions, like holes gradually opening in a misty curtain. Over time, as more galaxies formed and more stars ignited, these ionized bubbles expanded. Some overlapped. Some joined with neighboring bubbles. Slowly, the neutral hydrogen between galaxies was eaten away by spreading light. The process was uneven, gradual, and probably messy, shaped by where early galaxies formed, how bright they were, how gas was distributed, and how easily ultraviolet photons could escape from those galaxies into intergalactic space. Reionization was not a single switch being flipped. It was more like dawn arriving through broken cloud, with bright regions widening until the whole sky had changed. The main driver of reionization was ultraviolet radiation. Ultraviolet photons carry more energy than visible light, and the most energetic of them can ionize hydrogen by knocking electrons free from atoms. Massive young stars are especially strong sources of ultraviolet radiation. Since the first generations of stars were often hot and bright, they were natural contributors to this transformation. Early galaxies, filled with clusters of young stars, may have supplied much of the radiation needed to reionize the universe. There may have been other contributors as well. Early black holes could have played a role, especially if gas falling into them produced intense radiation. When matter spirals into a black hole, it can heat up enormously, before crossing the event horizon, releasing energy from the surrounding accretion disk. Some early black holes may have powered active galactic nuclei, bright central regions of young galaxies. Scientists still study how much these sources contributed compared with ordinary star-forming galaxies. The balance matters, because it tells us what kinds of objects were most responsible for ending the cosmic dark ages. One particularly useful type of object for studying this era is the quasar. A quasar is an extremely bright active galactic nucleus, powered by material accreting onto a supermassive black hole. Quasars can outshine their host galaxies, making them visible across enormous distances. Their light passes through intergalactic hydrogen on the way to Earth, and that hydrogen leaves marks on the quasar's spectrum. In this way, quasars act like backlights shining through the early universe, revealing what the gas between galaxies was like when the light passed through it. The Sloan Digital Sky Survey has been one major project involved in finding distant quasars and mapping large parts of the sky. By identifying quasars from the early universe, astronomers can study how much neutral hydrogen remained at different times. This is not easy, because the light has travelled for billions of years, stretched by cosmic expansion and filtered through many layers of intervening matter. But distant quasars remain among the most valuable tools for probing the end of the cosmic dark ages. One important observational feature connected to this work is the Gunn-Peterson trough. This is a dark absorption region seen in the spectrum of a distant quasar where neutral hydrogen absorbs much of the light at particular wavelengths. In simple terms, if a quasar's light passes through a universe containing a significant amount of neutral hydrogen, some of that light is removed before it reaches us. The Gunn-Peterson trough is therefore a clue that neutral hydrogen was still present along the line of sight. By studying these absorption features in very distant quasars, scientists can learn about when and how the universe became mostly ionized. The name comes from James Gunn and Bruce Peterson, who predicted this effect in the 1960s. Their work showed that even a small amount of neutral hydrogen in intergalactic space could produce strong absorption in the light from distant quasars. Later observations found evidence of this absorption in very distant objects, helping astronomers trace the changing state of hydrogen across cosmic time. It's a beautiful example of how absence can become evidence. A missing part of a spectrum can reveal something real about gas that existed more than 12 billion years ago. Cosmic reionization brought the universe into a new state. Before stars, the cosmos had passed from hot plasma to neutral atoms, then into long darkness. With the first stars and galaxies, light returned, but it did more than illuminate. It heated gas. It ionized hydrogen. It carved bubbles into the neutral intergalactic medium. It changed how radiation moved through space. The universe before stars was transformed not simply because light appeared, but because that light altered the matter it touched. This is why reionization is such a crucial part of the story. It marks the fading of the last widespread fog left from the early universe. The first stars ended the deepest darkness locally, but reionization changed the space between galaxies on a cosmic scale. Light was no longer just a signal moving through the universe. It had become an agent of transformation. The young cosmos was growing brighter, more structured, and more chemically complex, while the old neutral fog slowly gave way to a universe where galaxies could shine across expanding space. The universe before stars cannot be photographed in the simple way a nearby galaxy can be photographed. There were no bright spiral arms to capture, no glittering star fields, no glowing nebulae shaped by newborn suns. Much of that era was dark, invisible light, and the objects that eventually ended it formed so far away and so long ago that their signals arrive faint, stretched, and difficult to separate from everything between them and Earth. Scientists are trying to study a time that cannot be seen directly in ordinary light. which is rather like trying to reconstruct a vanished forest from pollen, shadows, distant echoes, and one very suspicious footprint. But this does not mean the era is unknowable. The universe keeps records. Some are written in ancient light, some are hidden in the faint radio signals of hydrogen, some are preserved in the chemistry of extremely old stars, some are reconstructed through computer simulations that combine known physics and test it against observation. To study the universe before stars, scientists use all of these clues together, building a picture piece by piece rather than relying on one perfect view. One of the most important records is the cosmic microwave background. This is the ancient afterglow released when the universe first became transparent, long before the first stars had formed. It is not starlight. It is older than starlight. It comes from the time when electrons joined with atomic nuclei to form neutral atoms, allowing photons to travel freely across space. Today, that light has been stretched by cosmic expansion until it appears as faint microwave radiation coming from every direction in the sky. The cosmic microwave background is sometimes described as a map of the baby universe, though the word baby is doing a lot of gentle work there. It shows the universe when it was about 380,000 years old, which is young compared with its present age of nearly 14 billion years. This map is remarkably smooth, but not perfectly smooth. Tiny temperature variations appear across it, showing slight differences in density in the early universe. Those small unevennesses later became the seeds of cosmic structure. Gravity amplified them over time, helping form dark matter halos, gas clouds, stars, galaxies, and galaxy clusters. Measurements of the cosmic microwave background by missions such as the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck Space Observatory have allowed scientists to refine the basic contents and history of the universe. These measurements help estimate the amount of ordinary matter, dark matter, and dark energy, as well as the overall geometry and expansion history of the cosmos. The cosmic microwave background does not show the first stars directly, but it reveals the conditions from which they eventually formed. It is the opening page of the visible universe, written in faint warmth. Another major method is 21 centimeter cosmology. This is the effort to detect signals from neutral hydrogen before and during the era of reionization. Neutral hydrogen can emit or absorb radiation connected to a very specific internal transition, often called the 21 centimeter hydrogen line. In nearby galaxies, this signal is extremely useful for mapping hydrogen gas. In the early universe, it offers something even more ambitious, a way to trace the neutral hydrogen that filled space before the first stars, and then watch how that hydrogen changed as stars and galaxies began ionizing it. This signal is very difficult to measure. By the time radiation from ancient hydrogen reaches modern instruments, cosmic expansion has stretched it to much longer radio wavelengths. The signal is faint, and it has to be separated from stronger foreground signals from the Milky Way, human radio interference, Earth's ionosphere, and many other complications. The early universe does whisper, but it whispers through several walls, across billions of years, while modern civilization loudly checks its phone. Several major instruments and observatory projects are designed to search for these radio clues. The Hydrogen Epoch of Reionization Array studies low-frequency radio signals from the early universe, aiming to detect patterns from neutral hydrogen during the time when the first stars and galaxies were changing intergalactic gas. The Low-Frequency Array, a large radio telescope network based mainly in Europe, also contributes to early universe radio studies. The Square Kilometre Array Observatory, an enormous international radio astronomy project, is expected to become one of the most powerful tools for exploring faint hydrogen signals from cosmic dawn and reionization. There is also the experiment to detect the global epoch of reionization signature, often discussed in connection with broad hydrogen signals from cosmic dawn. Its reported detection attracted great interest because it suggested a possible signal from the era when the first stars affected the hydrogen around them, but the measurement is difficult and debated. Other experiments have not simply settled the matter, and scientists continue to examine whether the signal truly came from the early universe or from some foreground or instrumental effect. This is how careful science should behave. Exciting claims are not ignored, but they are tested, challenged, repeated, and sometimes left patiently unresolved. Distant galaxies provide another route into the darkness. Telescopes such as the James Webb Space Telescope search for extremely early galaxies whose light has travelled for more than 13 billion years. Because that light has been redshifted by cosmic expansion, it often arrives in infrared wavelengths. These galaxies are not the universe before stars, but they are close to the period when the first stars and galaxies were beginning to transform space. By studying their brightness, colours, spectra, and distances, astronomers can estimate how rapidly galaxies formed and how much they contributed to reionization. Very old stars also preserve clues. Some ancient stars in the Milky Way and nearby dwarf galaxies contain extremely small amounts of heavy elements. Their chemical patterns can reveal what kind of supernovae enriched the gas from which they formed. If a star formed from material seeded by one of the first stellar explosions, its atmosphere may still carry a chemical fingerprint of that event. This work is sometimes called stellar archaeology, because scientists are using surviving stars as fossils of earlier generations. Computer simulations are essential as well. The first stars and galaxies formed through processes that are too large, too distant, and too ancient to watch directly in full detail. Simulations allow scientists to model how dark matter clumped, how gas fell into halos, how molecular hydrogen cooled the gas, how the first protostars formed, how radiation affected nearby hydrogen, and how supernova spread heavy elements. These models must combine gravity, gas dynamics, radiation, chemistry, dark matter, and sometimes magnetic fields. It is a demanding mixture, rather like asking a computer to cook the universe from scratch, while remembering every ingredient down to the particle level. The best simulations are not just cosmic animations, they are tools for testing ideas. Scientists compare them with observations from the cosmic microwave background, early galaxies, quasar absorption, hydrogen signals, and ancient stellar chemistry. When models and observations agree, confidence grows. When they disagree, the models are revised, or the observations are examined more carefully, or sometimes both. The uncertainty is not a weakness, it is part of the method. The era before stars is therefore partly reconstructed rather than directly seen. Its story comes from ancient radiation, faint radio possibilities, distant infrared galaxies, chemical fossils, quasar spectra, and theoretical modelling. Some parts are well established. The universe expanded and cooled. It formed neutral atoms. It entered a dark period. Gravity gathered matter. The first stars and galaxies eventually appeared. Other details remain uncertain, including the exact masses of the first stars, the timing of the earlier star formation, and the full pattern of reionization. That uncertainty gives this era its quiet power. Scientists are not staring at a clear photograph and naming everything in it. They are listening to the oldest clues the universe still carries. The darkness before stars has not vanished completely. It has been stretched, scattered, hidden, and folded into signals that are difficult to read. But through them, the universe still tells part of its earlier story, not in bright images, but in afterglow, hydrogen, gravity, chemistry, and the patient work of evidence. The universe before stars can seem at first like an absence. No galaxy shining across space, no sun, no planets catching daylight, no constellations, no nebulae, no bright clusters, no familiar night sky. But this dark universe was not a failure to become interesting. It was the necessary foundation for everything visible that followed. The darkness was not empty. It was a real physical era, full of matter, radiation, dark matter, gravity, cooling, and slow preparation. To see why it matters, the whole journey has to be gathered gently back together. The universe began in a hot, dense, expanding state. Space itself expanded, and as it expanded, the universe cooled. From that cooling came the first elementary particles, including quarks, electrons, neutrinos, and photons. Quarks combined into protons and neutrons. Then Big Bang nucleosynthesis formed the first atomic nuclei, mainly hydrogen nuclei and helium nuclei, with only tiny traces of lithium. These were simple ingredients, but they would become the raw fuel of the first stars. For a time, the universe remained a glowing plasma. Light existed, but it could not travel freely because free electrons scattered photons again and again. Then recombination allowed electrons to join with nuclei, forming neutral hydrogen and helium atoms. This made the universe transparent. Photons were finally released into open space, creating the ancient afterglow now known as the cosmic microwave background. That light still fills the universe today, stretched into microwave radiation by the expansion of space. But after that first glow faded into longer wavelengths, there were still no stars. The universe entered the cosmic dark ages, an interval filled mostly with neutral hydrogen, helium, dark matter, and tiny density differences slowly growing under gravity. It was dark because no stars or galaxies had formed yet, not because nothing was happening. In fact, something essential was happening. The universe was learning how to gather. Ordinary matter alone didn't instantly become stars. Hydrogen and helium did not simply clump together the moment atoms formed, as though the universe had suddenly decided to try interior lighting. Structure required the combined effects of expansion, gravity, cooling, dark matter, and time. Expansion set the background conditions. Gravity pulled matter inward. Dark matter formed invisible halos that acted as gravitational wells. Gas fell into those wells. Cooling allowed the gas to lose energy, reduce pressure, and collapse more deeply. Without all of these processes working together, the first stars could not have formed. Dark matter was especially important because it began building structure before ordinary gas could easily do so. It did not shine, but it shaped where shining objects would later appear. It formed the invisible skeleton around which the visible universe would grow. Hydrogen and helium gathered inside dark matter halos, and in the densest places molecular hydrogen helped the gas cool. From those cooling clouds came dense protostellar cores. When temperature and pressure rose high enough, nuclear fusion began, and the first stars ignited. Those first stars, known as population 3 stars, changed the universe profoundly. They were likely massive, hot, short-lived, and rich in ultraviolet radiation. Their light heated surrounding gas and began ionizing neutral hydrogen. Inside their cores, stellar nucleosynthesis created heavier elements that had barely existed before: carbon, oxygen, nitrogen, silicon, iron, and others. When many of those stars died, their supernova scattered these new elements into space. The universe was no longer chemically pristine. It had begun the long process of enrichment. That enrichment mattered for everything that came later. The first stars did not instantly fill the cosmos with heavy elements, but they began a chain of stellar generations. Each generation formed from gas, lived, changed matter in its core, and returned some of that material to space, Over time, galaxies became more chemically complex. Gas clouds cooled more efficiently. Later stars formed in richer environments. Around some of those stars, planets could assemble from dust and rock. In rare places, those planets could hold atmospheres, oceans, and the chemistry of life. The first galaxies grew from the merging of smaller halos, gas clouds, and early star-forming regions. They were probably irregular and turbulent, very different from elegant modern spirals like the Milky Way. But they were crucial. They gathered stars together. They recycled gas. They spread heavy elements. They sent radiation into intergalactic space. Eventually, through cosmic reionization, energetic light from early stars and galaxies stripped electrons from neutral hydrogen across vast regions of the universe. Light did not merely appear in the darkness, it changed the darkness. That is why the dark universe matters. It was not a waiting room before the real story began. It was part of the real story. It was the era in which the universe cooled enough to make atoms, became transparent enough to release its first ancient light, and gathered enough structure for stars to form. Darkness, here, was not emptiness. It was preparation. It was the quiet physical interval between the first glow and the first starlight. Every familiar object owes something to that time. The Milky Way depends on earlier structure. The Sun depends on generations of stars that enrich the gas from which it formed. Earth depends on heavy elements made inside stars and spread by stellar deaths. Oceans depend on oxygen. Rocks depend on silicon, magnesium, iron, and many other elements. Living chemistry depends on carbon, nitrogen, phosphorus, and more. None of these were available in abundance before stars. The dark universe held the simple ingredients, but stars made those ingredients richer. Modern astronomy lets scientists study this history by looking outward and backward at the same time. Because light takes time to travel, distant objects are seen as they were long ago. A nearby star shows a relatively recent past. A distant galaxy shows a much older one. The cosmic microwave background shows the universe when it first became transparent. The most distant galaxies reveal stages when the cosmos was young and still changing rapidly. Astronomy is not only the study of faraway places, it is the study of ancient time arriving as light. So the darkness before stars has not disappeared entirely. Its evidence still reaches us in faint radiation, distant galaxies, old hydrogen signals, chemical traces, and the large-scale structure of the cosmos. The universe before stars was quiet only in appearance. Beneath that darkness, expansion, gravity, cooling, and matter were preparing everything that would one day shine. The universe before stars was not a blank prelude, waiting for the real story to begin. It was not a mistake, or a pause, or an empty stage before the lights came on. It was a long and essential chapter in cosmic history, a quiet era in which the conditions for everything visible were slowly being prepared. Before there could be constellations, galaxies, planets, oceans, forests, or anyone looking up in wonder, the universe first had to pass through darkness. It began hot, dense, and expanding. Space stretched, and as it stretched, the universe cooled. Energy settled into particles. Quarks became protons and neutrons. Big Bang nucleosynthesis formed the first simple nuclei, mostly hydrogen and helium. Later, electrons joined with those nuclei to make neutral atoms, and the universe became transparent. The ancient glow from that moment still surrounds us as the cosmic microwave background, faintly cooled by nearly 14 billion years of expansion. Then came the Dark Ages, not empty, but dim. Neutral hydrogen and helium filled space. Dark matter gathered into invisible halos. Tiny density differences slowly became more important. Gravity pulled, gas collected. Cooling allowed matter to collapse more deeply. In that long quiet, the first star-forming clouds began to take shape, hidden inside darkness that was not asleep, only patient. When the first stars finally ignited, they were not simply light switching on. They were engines of transformation. Their nuclear fusion produced energy. Their ultraviolet radiation heated and ionized nearby gas. Their interiors began making heavier elements that had barely existed before. When many of them died, their explosion scattered carbon, oxygen, silicon, iron, and other elements into space. The first stars changed the chemistry, temperature, structure, and future possibilities of the universe. From them came the path toward the first galaxies, then richer generations of stars, then planets, then the materials needed for atmospheres, oceans, rocks, and living chemistry. The universe did not become complex all at once. It learned complexity slowly, through expansion, gravity, cooling, fusion, stellar death, and renewal. A galaxy is not just a collection of stars. It is the outcome of a long chain of earlier conditions, many of them laid down before any star had ever shone. Many details remain under active study. Scientists are still investigating the exact masses of population 3 stars when the first star formation began, how common different kinds of early supernova were, and how cosmic reionization unfolded across the universe. The broad outline is strong, but the earliest light still keeps some of its secrets. That is part of what makes the subject so quietly powerful. Every familiar starry sky rests upon an earlier age when there were no stars at all. Before the Milky Way, before the Sun, before Earth turned under daylight and night, there was a universe of simple atoms, invisible gravity, fading radiation, and slowly gathering matter. The first light was not the beginning. It was what the darkness had been preparing.